Hello there, and welcome to the Cosmographer. 1,715 star systems have been in a position to watch the Earth cross the face of the Sun since the beginning of recorded human civilization, and 75 of them have held that view for the entire century in which we have been broadcasting radio. That is number 19 on tonight's list, and it is one of 20 real, published, still open reasons to think we might not be alone. They are not ranked by how likely each one is, and they are not ranked by how strange each one is. They are ranked by a single rule: how soon we find out. Number 18 was a signal that lasted 72 seconds in 1977 and has been looked for about 50 times since without ever returning. Number 16 sped up as it left the solar system with nothing visibly coming off it, and is now beyond every telescope on Earth. Number 10 is a moon where methane falls as rain and collects into seas hundreds of meters deep. And number 7 is a rock that has already been drilled, already been sealed, and is lying on the ground on Mars with no funded way home. Get comfortable and settle in. If 3 hours of the universe is your idea of a good night, hitting like and subscribe genuinely helps this channel. Because by the end of this list, the closest thing we have to an answer will turn out to be something already sitting on a shelf. Let's begin at number 20. Number 20, the silence itself. There are 20 entries on this list, and every one of them is a real, published, still open reason to think that we might not be alone. None of them is proof. All of them are on the table tonight because serious people, using serious instruments, have not been able to close the file. They are not ranked by how likely each one is to turn out to be somebody else. They are not ranked by how strange they are. They are ranked by one thing only, and it is worth stating plainly before we begin, because it is the shape of the next 3 hours. They are ranked by how soon we find out. Number 20 is an idea built so carefully that no observation could ever settle it. Number 1 is a set of evidence that is already on Earth, already catalogued, already sitting in a sealed cabinet in a building in Texas, where the only thing standing between us and the answer is how quickly a small number of people can look at it. Everything in between is a slow walk from one to the other. As the numbers fall, the horizon comes closer. So we begin with the quiet. The universe is very large, and it is not saying anything. That observation is old, and the most discussed explanation for it is the one people usually call the dark forest. The full version of it comes from a novel published in Chinese in 2008 and in English in 2015, and it is worth saying at the outset that it is fiction. But the reasoning inside it is a formal argument, and it has been taken seriously in the academic literature ever since. The argument rests on 2 starting assumptions. The first is that survival is the primary need of any civilization. The second is that civilizations grow continuously, while the total amount of matter in the universe stays fixed. On their own, those 2 statements are not alarming. What makes them into something else is a pair of mechanisms. The first mechanism is called the chain of suspicion. 2 civilizations separated by light years cannot verify each other's intentions. They also cannot verify what the other one believes about their intentions. And they cannot verify what the other one believes about what they believe. There is no way to short-circuit that loop when a single exchange of messages takes decades or centuries, so trust never arrives. The second mechanism is the technological explosion. A civilization that is harmless today can leapfrog you inside the time it takes light to cross the distance between you. So the neighbor you can safely ignore this century is not necessarily the neighbor you can safely ignore in 500 years, and you have no way of checking. Put those together, and you get the conclusion. Anyone who reveals their position is treated as a potential threat by everyone who notices, and some of those who notice will act. So nobody speaks. The image the novel uses is of armed hunters moving quietly through trees, each one listening, none of them willing to be the first to make a sound. The idea did not begin with that novel, and it is fairer to say so. Fred Saberhagen was writing stories about self-replicating killing machines in the 1960s. Greg Bear, in 1987, described the galaxy as a jungle full of hawks, where anything that does not know enough to keep quiet gets eaten. And in the refereed literature there is a paper by David Brin, published in the Quarterly Journal of the Royal Astronomical Society on the 1st of September 1983, under the title The Great Silence. It is a review rather than an argument, and it lays out the deadly machine scenario alongside every other explanation on offer. Brin's own summary of the field is the useful part. He described it as split between those looking for optimistic excuses for the absence of neighbors and those who cheerfully accept the silence as evidence that we are alone in an open frontier. So why is this number 20 rather than higher? Because of four things. The first is the strongest, and it is that hiding does not work. Earth's atmosphere has been rich in oxygen for something on the order of 1 billion years, and that oxygen has been remotely detectable for all of it. Waste heat cannot be suppressed either. Any civilization using large amounts of energy has to put that energy somewhere, and thermodynamics says it comes out as infrared. Staying quiet defeats deliberate broadcasting and nothing else. You can stop shouting. You cannot stop being a planet. The second objection is called uniformity of motive. The scenario requires that essentially every independent civilization, arising separately, under different conditions, with different histories, arrives at the same fear-driven strategy and then keeps to it. One defector inside detection range breaks the whole thing. And the chance that there is a defector rises with the number of civilizations, which means the argument works worst in exactly the case where it is supposed to matter most. The third is that a galaxy running on this strategy should show evidence of it. Systems that have been sterilized. Engineering on a scale that leaves a mark. Something. We do not see any of that. And the fourth objection is the one that puts this entry at the bottom of the countdown. The hypothesis is not falsifiable. Silence is equally consistent with hiding, with extinction, with rarity, with life that never became technological, with disinterest, and with nothing more exotic than distance. A proposal that explains every possible outcome is closer to a way of looking at the world than it is to a testable model. It is a question with no appointment. There is no instrument that would settle it, no mission that could check, no year on the calendar when the answer arrives. Which is not to say the silence itself is unmeasured. It is measured, and the numbers are worth hearing, because they turn something that sounds like a mood into something you can put a figure on. There is a project called the G-HAT survey, led by Jason Wright and Roger Griffith, which searched roughly 100,000 galaxies in mid-infrared data from the WISE Space Telescope. The reasoning was simple. A civilization using a significant fraction of the starlight in its own galaxy would have to radiate that energy as heat, and heat glows in the mid-infrared. Their result: not one galaxy in 100,000 reprocesses more than 85% of its starlight into the infrared. 50 of them are consistent with more than half, and every one of those 50 has an ordinary explanation involving bursts of star formation or an active black hole at the center. 100,000 galaxies. Nothing. Closer to home, the Breakthrough Listen program launched in 2015 with $100 million behind it. One early survey searched 1,327 nearby stars between 1.1 and 3.45 gigahertz using the Green Bank telescope in West Virginia and the Parkes dish in New South Wales. The pipeline produced more than 51 million raw detections above threshold. Automated vetting narrowed that to 6,154 groups worth a second look. Human inspection narrowed that to 0. A later search used a deep learning method on 820 stars across more than 480 hours of Green Bank time. It flagged 8 signals of interest. The telescope went back to all 8. None of them was there. The extragalactic arm of the same program searched 97 nearby galaxies and ruled out transmitters at around 10 to the 26th watts, which is roughly the power scale of something using the entire output of a star. And there is one more result that belongs here, because it is quietly the strangest thing in this entire entry. In June 2016, David Kipping and Alex Tichy published a paper in Monthly Notices of the Royal Astronomical Society working out what it would actually cost to hide a planet. Not metaphorically. In watts. Their answer is almost comically modest. To erase Earth's transit from a survey like Kepler's, using an optical laser array to fill in the dip as the planet crosses the star, you would need about 30 megawatts, running for roughly 10 hours a year. To hide only the oxygen, the biosignature specifically, and nothing else, takes about 160 kilowatts. A full cloak, effective at every wavelength, takes about 250 megawatts. Those are power levels a mid-sized power station on Earth could supply today. The same paper points out the inverse, which is more interesting. The transit could be deliberately distorted into a shape that nothing natural produces and used as a beacon. If anyone has ever done that, the evidence would already be sitting in archived transit data that we have collected and not yet examined for that particular thing. In February 2015, 28 scientists and technologists signed a public statement about deliberately broadcasting our position. Among them were David Brin, the astronomer Jeffrey Marcy, Elon Musk, and 2 of the people running Breakthrough Listen. The operative sentence is short. Intentionally signaling other civilizations raises concerns for all the people of Earth, and a worldwide discussion must happen before any message is sent. Their summary of it is the line worth keeping. It is prudent to listen before we shout. That is the entire content of number 20. The quiet is real. It has been measured across 100,000 galaxies and thousands of stars, and the most famous explanation for it is one that no telescope will ever confirm or refute. Everything else on this list can, in principle, be settled. That is why this one goes first, and why the 19 entries below it get progressively closer to an answer. But the next sign is not an argument at all. It is a list of names, and every star on it has already had a clear view of us. Number 19. The stars that can already see us. The zoo hypothesis is the idea that we have already been found, and that whoever found us decided to leave us alone. It sits high on this list for the same reason the silence does. If someone has resolved to be undetectable, then their undetectability is not evidence of anything, and there is no experiment that changes that. But this entry comes with something the last one did not have. It comes with a catalogue. We know, by name, which stars have had a clear geometric view of the Earth, and for how long, and which ones are getting that view next. Start with the paper. John Ball published it in the journal Icarus in July 1973. It is 3 pages long. The abstract reads, more or less exactly, that extraterrestrial intelligent life may be almost ubiquitous, and that the apparent failure of such life to interact with us may be understood in terms of the hypothesis that they have set us aside as part of a wilderness area or a zoo. Ball's own restatement of it is sharper. "The only way to understand the apparent non-interaction," he wrote, "is to suppose that they are deliberately avoiding it." And his paper is honest about what kind of claim that is. It is a thought experiment about how perfect the isolation would have to be, not an assertion that anyone is out there. Martin Fogg extended the idea in the same journal in February 1987, calling it the interdict hypothesis. His version is not one zookeeper acting alone, but a negotiated arrangement among the first civilizations to arise in the galaxy, quarantining developing worlds until they are considered mature. Fogg ran simulations of when those first civilizations would have appeared and how they would have met. The objection is the same one that sank the entry before this. Every advanced civilization within range has to adopt the rule independently and then keep to it permanently. Jason Wright and colleagues gave the general form of this problem a name. They call it the monocultural fallacy, and it applies to every proposal that requires the whole galaxy to want the same thing. So much for the argument. Now the catalogue, which is real. Lisa Kaltenegger and Jackie Faherty published it in Nature on the 23rd of June 2021, using positions and motions from the Gaia spacecraft. Their question was narrow and clever. We find most of our exoplanets by watching a star dim slightly as a planet crosses in front of it. That only works if you are sitting in the narrow band of sky where the planet's orbit lines up edge-on from your point of view. So which stars are sitting in the band that would let them see Earth cross the Sun? The answer is 2,034 star systems, across a window of 10,000 years, 5,000 back and 5,000 forward. Every one of them lies within 326 light-years, which is a small neighborhood in a galaxy 100,000 light-years across. 1,715 of those have held that view since roughly the beginning of recorded human civilization. 319 more move into position over the next 5,000 years and are not there yet. 117 of the 2,034 sit within about 100 light-years of us. 75 of those have been in position for the entire century in which we have been broadcasting radio. 7 of the catalogued systems are known to have planets, and 2 of those are worth naming. Ross 128 is a red dwarf about 11 light-years away in Virgo. It watched Earth transit the Sun for 2,158 years, starting about 3,000 years ago, and it lost that view roughly 900 years ago. If anyone was ever looking from there, the geometry closed on them around the time Europe was building its first cathedrals. The other is TRAPPIST-1, 45 light-years away, with 7 Earth-sized planets, and we will come back to it much later tonight. It cannot see us. It enters the transit zone in 1,642 years and then holds the view for 2,371. Kaltenegger's own summary of the result is the calmest way to put it. Even the closest stars generally spend more than 1,000 years at a vantage point where they can see Earth transit. Now for the correction, because this is the point where the popular version of the story goes wrong. You have probably heard about the radio bubble. Our earliest broadcasts left in the 1920s, so the leading edge of them is now about 119 light-years out. That sphere encloses Alpha Centauri, Sirius, and Vega. All of that is true as geometry, and almost useless as a claim about detection. A technical assessment by the SETI Institute concluded that an alien counterpart of our largest radio telescopes could not detect an ordinary television broadcast, even from the nearest star system. One published estimate put it more bluntly still. Picking up Earth's leakage from a single light-year away would need a receiving dish about 900 kilometers across. The rigorous version of the calculation was done by Ramiro Saide, Michael Garrett, and Nalini Hirilal Isur, published in Monthly Notices of the Royal Astronomical Society in June 2023. They took a public database of mobile phone tower locations, gridded the Earth's surface, integrated the antenna patterns, and worked out what our mobile networks look like from 3 specific nearby stars. The peak power radiated into space came to about 4 gigawatts, and it comes from mobile towers on the east coast of China, seen from a red dwarf called Lalande 21185. The leakage sweeps around as the Earth turns, rising and falling with the rotation. And their conclusion was that a civilization within 10 light-years, using a telescope as good as Green Bank, could not currently detect it. There is a further irony in the numbers. Earth is getting quieter, not louder. Fiber optic cable, digital encoding, directional antennas and satellite links all leak far less than 20th century analog broadcasting did. Our loudest decades are behind us. Which brings us to the best experiment anyone has ever run on this question, and it was run on ourselves. In December 1990, the Galileo spacecraft passed close to Earth on its way out to Jupiter, using our gravity for a speed boost. Carl Sagan and his colleagues realized that this was an opportunity nobody had taken. Turn the instruments around. Point them at the Earth. Then ask a simple question. If this spacecraft had never been here before and knew nothing, what would it conclude? The paper ran in Nature on the 21st of October 1993, and the authors described it in their own words as a control experiment for the search for life. Here is what Galileo found. Abundant molecular oxygen in the atmosphere. A pigment covering large parts of the surface with a sharp absorption edge in the red, which is the signature of chlorophyll and which we call the red edge. Methane present in extreme thermodynamic disequilibrium, coexisting with all that oxygen when it should have been consumed long ago. Those 3 findings say that something is alive down there. They do not say anything about intelligence. The 4th finding does. Galileo detected narrowband radio emission at fixed frequencies between about 4 and 5 megahertz, isolated both in frequency and in time. Nothing in the natural world produces that. The authors concluded it could only have come from a technological civilization. So the honest accounting for number 19 is this. 2,034 star systems have had, or will have, a clear line of sight to Earth crossing the face of the Sun. From that vantage point, with a telescope somewhat better than ours, they could measure our oxygen and our chlorophyll and our disequilibrium methane, and they could have been doing it for a very long time, because those signatures are around 1 billion years old. Whether they could hear us is a different and much less flattering question, and the answer appears to be probably not, at least not yet, and possibly not ever, because we are turning the volume down. That is a list of who could have looked. The next sign is the one time something looked back, for 72 seconds, and never again. Number 18, 72 seconds. In August, the most famous unexplained result in the history of the search for other intelligence lasted 72 seconds, happened on a summer night in Ohio, and has never happened again. It is at number 18 for that second reason. A one-off event with no repeat has no route to an answer. There is nothing to go back to. Here is what happened. On the 15th of August 1977, at 16 minutes past 11 at night, Eastern Time, a radio telescope called Big Ear recorded a burst of narrowband radio energy from the direction of Sagittarius. Big Ear belonged to Ohio State University and sat on the grounds of Perkins Observatory in Delaware, Ohio. Its data went through an IBM 1130 computer and came out on line printer paper, in columns, to be read by hand. Picture the moment it is actually found, because it is not what most people imagine. It is a few days later, and a man is sitting at a table with a stack of folded printer paper in front of him. The room is ordinary. There is a fluorescent light overhead and a red pen in his hand. He is a volunteer. He is not being paid for this. His job tonight is to run his finger down column after column of characters, produced by a machine that has been reading the sky for 4 years and has never once printed a letter higher than D. He works down the page. Spaces. Ones. A 2. Spaces again. This is what the sky looks like, over and over, for 4 years. Then his finger stops. 6. E. U. U. J. 5. He goes back to the top of the column and reads it again, more slowly, because the first reading cannot be right. The characters do not change. He checks the timestamp. He checks the channel. The numbers climb, hold, and fall away, and the shape of them is the shape of something sitting still in the sky while the earth turns past it. And then he takes the red pen, draws a circle around 6 characters of ordinary printout, and writes a single word in the margin beside them. That word is the only reason any of us know this ever happened. Now for the correction that has to be made every single time, because the popular version of this story is wrong in a specific and important way. The string he circled, 6, E, Q, U, J, 5, is not a message. It is not code. It is a column of signal strengths, 1 character per 10-second sample, written in a compressed notation that the survey used to save paper. A blank space means the signal was between 0 and 1 standard deviation above the background noise. The digits 1 through 9 mean 1 through 9 standard deviations. Then, because there are no more digits, the notation continues into letters. A means 10 to 11. B means 11 to 12. And so on. U means 30 to 31. So the peak of that signal was about 30 standard deviations above the background, and the character U was the highest single character produced in 22 years of that survey. Not a word. A measurement. The next detail is the strongest argument that the signal came from the sky rather than from a car park. Big Ear could not slew. It was a transit instrument. It could be tilted in altitude, and after that it relied entirely on the rotation of the Earth to sweep across the sky. That meant any fixed point in space stayed inside its beam for exactly 72 seconds, and no longer. The signal rose for about 36 seconds, peaked and fell away for about 36 seconds. That is not a coincidence, and it is not a shape that interference makes. That is the telescope's own sensitivity curve, traced out perfectly by something that was holding still while the Earth turned underneath it. It was also extraordinarily narrow. The whole thing sat inside a single 10 kHz channel out of 50, which is a fractional bandwidth of about 1,000th of 1%. In 1977, nothing in nature was known to broadcast that narrowly. Nature is generally messy across frequencies. Transmitters are not. The frequency itself is disputed, and the reason is a typing error. The receiver's first local oscillator was specified at 1 value, and a purchasing typo delivered 1/10 of a megahertz high. The software was patched afterwards to compensate. John Krauss, the observatory's director, wrote down one figure in a summary he prepared for Carl Sagan. Eamon, correcting for the oscillator, published a different one in 1998, about 50 kHz above the rest frequency of neutral hydrogen. That rest frequency is the one Giuseppe Cocconi and Philip Morrison had argued in 1959 that anyone trying to be found would naturally choose, because it is the loudest natural frequency in the universe, and every radio astronomer everywhere has to be listening near it. Then there is the two-horn problem, and this one can never be fixed. Big Ear had two feed horns, pointing at slightly different patches of sky. Whatever it saw appeared in one of them and not the other, and the way the data was reduced destroyed the record of which. So there are two candidate positions on the sky, 3 minutes of right ascension apart and one declination. The region is in Sagittarius, northwest of the globular cluster M55, about 3.5 degrees south of the ecliptic. And there is one more consequence of that. If the signal was celestial, it should have swept into the second horn about 3 minutes later. It did not. So people went back to look, repeatedly and for decades. Eamon and the Big Ear team searched again in the months afterwards and kept searching. He later said they should have seen it again in about 50 attempts. Robert Gray searched with the Meta Array at Oak Ridge in 1987 and again in 1989. Paul Schuch used the 12-meter dish at Green Bank in July 1995. Gray and Kevin Marvel used the Very Large Array in New Mexico in 1995 and 96 and published the result in the Astrophysical Journal in 2001. That last one matters because the Very Large Array is far more sensitive than Big Ear ever was, which also weakens the idea that a faint source was briefly boosted by turbulence in the interstellar medium. Gray and Simon Ellingson ran 6 14-hour observations from a 26-meter dish in Tasmania in 1999. And in May 2022, Breakthrough Listen and the Allen Telescope Array ran the first coordinated campaign on newly proposed candidate stars in the field, an hour on one instrument and 35 minutes on the other. Every one of those is a null result. Nothing has ever come back. In 2016 and 2017, Antonio Paris proposed that hydrogen clouds around 2 comets had produced the signal. Robert Dixon, who had been on the original Big Ear team, dismantled it on 3 separate grounds. The comets were not in the beam at the right time. Comets do not emit anywhere close to that strongly at that frequency, and a slow, extended source gives no explanation whatsoever for one horn seeing it and the other not. That hypothesis is dead. The live hypothesis is newer, and it needs an honest label. Abel Mendez, Kevin Ortiz Ceballos, and Jorge Zuluaga at the Planetary Habitability Laboratory posted a paper in August 2024 proposing that the signal was a maser-like flare in the hydrogen line, coming from a small cold cloud of hydrogen that had been briefly energized by a passing burst of radiation from a magnetar. A second paper in August 2025 went back through decades of unpublished Ohio survey data and revised the numbers: a tighter position, a peak brightness above 250 Janskys, and a third frequency value different from both of the earlier ones. Neither paper has been through peer review. The note attached to the second one says, in plain words, that it will be submitted to a journal after incorporating feedback. And the objection to it is straightforward. No hydrogen mesa flare of that kind at that frequency has ever been directly observed anywhere in nature. The mechanism is inferred from laboratory work and partial theory. The clouds the team studied show that compact hydrogen can produce narrow features. They do not demonstrate the enormous, brief amplification that this would require. Big Ear itself is gone. The land lease expired at the end of 1997, and the site was sold for a housing development and an expansion of the neighboring golf course. Demolition began on the 22nd of April, 1998. The last pieces came down on the 7th of May, taken apart in 6 sections, each weighing more than 25 tons. It had operated since 1963. It catalogued about 20,000 radio sources, and it only became a full-time listening instrument in 1973 because the National Science Foundation had cut its survey funding the year before, which is a small and slightly absurd fact worth holding on to. The most famous candidate signal in the history of the field was found by a telescope that had been repurposed because it lost its grant. Eamon's own line about it, from 1997, is the right note to end on. He said he resists drawing vast conclusions from half-vast data. He also said, more than 20 years later, that he remains convinced the signal has the potential to be the first from another intelligence. Both of those can be true, and in his case, they clearly were. That signal came and went in 72 seconds. The next sign has been recorded thousands of times by the best sensors any government owns, and it is still unresolved for a reason that has nothing to do with what is in the sky. Number 17. The unidentified and the limits of the camera. The official record exists. That is the first thing to say, and it is worth saying calmly, because for most of the last 70 years, it did not. Governments now publish annual counts of unresolved sightings, and those documents are public, and they are dull in the way that useful documents usually are. The second thing to say is that when you read them carefully, they point at a conclusion that is not about the sky at all. The unexplained fraction tracks the quality of the data. Where the sensors are good, the cases close. Where the sensors are poor, they stay open. That is why this entry sits at number 17. The ceiling will not lift until the instruments change. Start with the 3 videos, because they are what most people have actually seen. The first is usually called the tic-tac footage, recorded on the 14th of November 2004 by aircraft from the USS Nimitz strike group, about 100 miles southwest of San Diego. The other 2 were both recorded in January 2015 off the east coast of the United States. All 3 had leaked years earlier through unofficial channels. On the 27th of April 2020, the Department of Defense officially released them. Their stated reason was that release revealed no sensitive capabilities and would clear up whether the circulating footage was authentic. Their characterization of what is in them was 1 sentence long. The aerial phenomena observed in the videos remain characterized as unidentified. Then the numbers. On the 25th of June 2021, the Office of the Director of National Intelligence published a preliminary assessment covering 144 reports, mostly from Navy personnel, between 2004 and 2021. Exactly 1 was identified with high confidence, and it was a large deflating balloon. 143 were not identified. That figure gets quoted constantly and almost always without the sentence that follows it, which is that the report is explicit, this is a data limitation result, rather than an anomaly claim. 18 incidents, described across 21 reports, involved objects that appeared to hold still in winds aloft, move against the wind, maneuver abruptly, or travel at considerable speed without any discernible means of propulsion. That 18 is the honest residue, and nobody serious dismisses it. In July 2022, the Pentagon established a dedicated office to resolve these cases. Its historical record report, published on the 8th of March 2024, found no evidence that any government investigation or review panel has ever confirmed a sighting as extraterrestrial technology, and no empirical evidence that anyone has reverse-engineered such technology. A metal fragment alleged to have come from an off-world craft was analyzed and found to be ordinary and terrestrial, with no exceptional properties. Their summary line is worth repeating. The overwhelming majority of reports, almost certainly, are the result of misidentification, and a direct consequence of the lack of domain awareness. The annual reports since then tell the real story in numbers. The report covering the 2024 fiscal year logged 757 reports, of which 485 fell inside the period, and 272 were older cases surfacing late. 118 cases were resolved during the period, and every one of them resolved to something ordinary: balloons of various kinds, birds, and drones. The most recent report, covering June 2024 to May 2025, was released around the 21st of July this year, several months past its statutory deadline. 319 new reports, 114 of them resolved, plus 256 older cases closed, 370 resolved investigations in a single year. Total case holdings now stand at 1,870. And here is the number that carries the whole entry. Of those resolutions, 238 came from one thing: a new three-dimensional modeling capability that identified them as satellites catching sunlight. Not a leak. Not a disclosure. A better model of where the satellites were. One case in that report remains open, and it deserves naming because it is the only maritime case of the year. Navy assets off the coast of Virginia reported roughly 100 airborne objects, together with 2 probable uncrewed surface vessels. The office has confirmed it is actively investigating. In September 2023, a 16-member independent panel, convened by NASA and chaired by David Spergel, published its own assessment. Its central finding is the sentence that ought to anchor this entire subject. The limited number of high-quality observations makes it impossible to draw firm scientific conclusions, because there is no body of consistent, calibrated, curated data to draw them from. The problem is instrumentation. The panel also found no evidence of extraterrestrial origin. 2 of the 3 famous videos now have specific technical explanations, and it is only fair to give them properly. In the second video, the object appears to rotate in mid-air. That rotation is widely attributed to the camera rather than the object. The sensor is mounted on a gimbal that rolls to keep a target centered while the host aircraft turns, and what is on screen is infrared glare from engine exhaust, which is larger than the aircraft producing it. When the gimbal rolls, the glare rotates with it. In the third video, the impression is of something skimming low and fast over the water. That impression is parallax. Using the camera's own displayed elevation angle and range, together with the aircraft's speed, the object works out to roughly 13,000 feet of altitude, and its computed ground speed falls to somewhere between 20 and 40 knots. Joshua Semeter's independent reconstruction landed at about 34 knots, which is a speed consistent with something drifting on the wind. Neither of those explanations identifies what the object was. They only remove the reason it looked impossible. And the counterweight belongs here too, delivered with the same fairness. The Nimitz encounter involved trained observers on more than one platform. Commander David Fravor, who submitted a written statement to a congressional committee in July 2023, described an object about 40 feet long, white, shaped like a lozenge, with no wings, no control surfaces, no exhaust plume, and no obvious means of propulsion, disturbing the water beneath it. Lieutenant Commander Alex Dietrich was flying the second aircraft and has spoken publicly about the same encounter. No formal investigation followed at the time. The radar operator on the cruiser had reported clusters of contacts over the preceding days that matched no known traffic pattern. The claim that those contacts dropped more than 80,000 feet in under a second is repeated everywhere, and it is worth being precise about it. That figure is operator testimony, and no radar tape supporting it has ever been released. So where does that leave number 17? It leaves it exactly where the panel put it. There is a residue of cases involving trained observers and multiple sensors that has not been explained, and it is small, and it is real. And there is a much larger population of reports that dissolves the moment somebody builds a better instrument or a better model. 238 satellites in a single year is what most of this looks like from the inside. Not a cover-up and not a revelation, but the slow, unglamorous work of building sensors good enough to tell us what we are actually looking at. Those objects were at least close enough to photograph. The next sign passed through the solar system once, was never photographed clearly, and is now beyond every telescope on Earth. Number 16, the one that got away. There is an object at number 16 that is not on this list because the physics is impossible. It is on this list because it left. On the 19th of October 2017, Robert Werrick was working with the Pan-STARRS 1 telescope on Haleakala on Maui when he found something moving through the survey data too quickly. Within days, the orbit was clear enough to be certain of one thing. Whatever this was, it had not come from here. It was given the designation 1I, and the letter I was invented for it. Interstellar. Language experts at the University of Hawaii at Hilo gave it a name that means, approximately, a messenger from afar arriving first. A scout. The orbit settles the question of origin and leaves everything else open. Its eccentricity is 1.20, and any value above 1 means the path is a hyperbola rather than an ellipse. It is not orbiting the Sun. It never was. It fell in, curved around and left. Its closest approach to the Sun was on the 9th of September 2017 at about 38 million kilometers, which is well inside the orbit of Mercury. Its inclination is 122 degrees, which means it came in retrograde against the direction everything else in the solar system travels. Far from the Sun's influence, its speed relative to the Sun was about 26 kilometers a second. It passed Earth on the 15th of October at about 24 million kilometers, which is roughly 60 times the distance to the Moon. That is close, and it is also a great deal further than any camera could turn into a picture. Which is where the strangeness begins, because everything we know about its shape comes from a single curve. Nobody ever resolved it. To every telescope on Earth, it was a point of light. But the brightness of that point varied by a factor of about 10 as it turned, which is 2.5 magnitudes, and which is the largest brightness variation ever recorded for a small body in the solar system. That variation implies a body whose longest dimension is at least 5 times its shortest, and possibly 6 or more. You have seen the picture. The long dark cigar, ridged like something machined. That is an artist's rendering, made quickly, and it is probably wrong. The best fits to the actual light curve favor something flattened, closer to a disc or a pancake than a rod. It was also tumbling. Not rotating cleanly about one axis, but wobbling about no stable axis at all, so that no single rotation period fits the data. 2 apparent frequencies show up in the light curve, close to each other and not resolving into anything simple. Tumbling like that is what you get after a collision. So somewhere in its history, in a system we will never identify, something hit it hard. Now for the measurement that made it famous. Marco Micheli and colleagues published in Nature in 2018. Tracking the object's path carefully, they found it was accelerating outward faster than gravity alone allowed. The significance was about 30 standard deviations, which in this business is not a marginal result. The excess fell off roughly as the inverse square of its distance from the Sun. In a comet, that is completely ordinary. Comets, outgas. The gas pushes. Every comet does it, and the effect is routinely modeled. But this object was not outgassing. Nothing was coming off it that anybody could see. The Spitzer Space Telescope stared at where it should have been for 30 hours and 2 minutes at a wavelength of 4.5 microns and detected absolutely nothing. From that non-detection came hard ceilings on what could be escaping. Dust production, no more than 9 kilograms per second. Carbon dioxide, no more than about 9 times 10 to the 22nd molecules per second. Carbon monoxide, an order of magnitude below that again. Those limits sit 2 to 3 orders of magnitude beneath what would be needed to push the object the way it was measurably being pushed. So it was accelerating, and there was no visible reason. Here is what Avi Loeb and Shmuel Bialy actually wrote, because this is usually mangled. Their paper in the Astrophysical Journal Letters in October 2018 asked a narrow physics question. Could sunlight pressure alone account for the acceleration? The answer was yes, but only if the object had a mass-to-area ratio of about 1/10 of a gram per square centimeter, which corresponds to a sheet somewhere between 3/10 and 9/10 of a millimeter thick. That is the paper. It is a calculation. The speculative part is a closing paragraph suggesting that such a thing could be a light sail, and specifically raising the possibility of debris from defunct equipment drifting between the stars rather than anything under active control. It was rebutted in Astronomy and Astrophysics in 2021. And it is worth noting that we build light sails ourselves. The Japanese Icaros craft flew on one in 2010, so the physics of the object is not exotic. Only the manufacturing would be. 3 natural explanations have been published since, and each one is interesting, and each one has been pushed back on. The first came from Darrell Seligman and Gregory Laughlin in 2020. Suppose the object were made of molecular hydrogen ice. Hydrogen sublimating from about 6% of the surface gives you exactly the right thrust with no visible coma, because hydrogen is invisible to the instruments that were watching. Progressive loss of mass would also carve out the extreme shape. Thiem Huang and Loeb refuted it within the year. Collisional heating in the cloud where such a body would have to form destroys hydrogen icebergs, and the object would have needed to start out absurdly massive to survive the journey. The second is the current frontrunner. Jennifer Bergner and Darrell Seligman published in Nature in March 2023. Take an ordinary water ice body. Over millions of years in interstellar space, cosmic rays break some of that water apart and produce molecular hydrogen, which gets trapped as microscopic bubbles inside the amorphous ice. As the body warms near a star, the ice anneals, reorganizing from a disordered structure into crystals, and the trapped hydrogen escapes. You get thrust, and you get no dust, and you get no visible coma. That would make it what is now called a dark comet. The model is contested. Critics argue it overestimates the surface temperature. The third came from Stephen Desch and Alan Jackson in 2021. Suppose it is a chip knocked off the nitrogen ice surface of a Pluto-like world in another system. Their numbers give a body 45 meters by 44 by 7.5, with a reflectivity of 64%, which is what you get from a nitrogen-covered surface, and which would make it one of the most reflective things ever seen passing through the solar system. It reproduces the acceleration and explains every non-detection. Amir Siraj and Loeb countered that the galaxy cannot produce enough Pluto-like worlds to supply such fragments, because there is not enough nitrogen to go around. Desch and Jackson replied that no error had been found in their work, only a competing estimate. Any one of those could be right, and there is no way to find out. Ride alongside it for a moment in late October 2017. Something roughly the length of a city block, flatter than it is long, is turning end over end with no rhythm at all. It catches sunlight and loses it, catches it and loses it, a factor of 10 between the bright face and the dark one, over and over, in silence. There is no tail behind it. There is no dust around it. Nothing is coming off it that any instrument can find. And it is speeding up, only slightly, only a nudge, but measurably more than the sun's gravity accounts for. Below and behind, on a planet it will never come near again, a few dozen telescopes are pointed at it for the last nights they will ever have. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. Today, it is about 53 astronomical units away, which is roughly 8 billion kilometers. Light from it takes over 7 hours to reach us. Its apparent magnitude is around 40, which is far beyond anything that has been built or seriously proposed. It crossed the outer Kuiper belt in late 2025 and should reach the edge of the Sun's influence around 2038. We did do the arithmetic on chasing it. A study called Project Lyra, run by the Initiative for Interstellar Studies since the 30th of October 2017, worked through the mission profiles carefully. The optimal launch window was 2021, and it has passed. The windows remaining in 2028, 2030, and 2033 give flight times of 16 to 17 years, with arrivals in 2047 and 2049. The required change in velocity is about 18 kilometers a second, achievable only by diving close to the Sun and burning at the bottom of its gravity well, which needs heat shielding of the kind the Parker Solar Probe carries, or by a powered flyby of Jupiter. No mission has been funded. It remains a paper study, and the paper gets slightly less useful every year. That is the shape of number 16, and it is worth sitting with. The first object ever confirmed to have come from another star was inside the reach of our instruments for roughly a week. The single measurement that would have settled what it was, a direct look at whatever was pushing it, is now permanently out of reach. Not because the question is difficult, because it left, and we were not ready. One is an anecdote. A single visitor, seen for a few nights and gone forever, tells you almost nothing. You cannot do statistics on one object. You cannot say what interstellar objects are typically made of, or how common they are, or whether this one was unusual, because you have nothing to compare it to. One visitor is not enough to conclude anything. The next sign has the opposite problem. There are thousands of them, and that is exactly why it is so hard to explain. Number 15. The bursts that keep a clock. Fast radio bursts arrive from across the universe, last about 1,000th of a second, and there are now several thousand of them on file. Most of the mystery around them has genuinely been solved, and this entry says so early because the part that is left is more interesting than the part that was answered. The first one was found in an archive. In 2007, Duncan Lorimer and his colleagues went back through observations recorded by the Parkes telescope in Australia on the 24th of July 2001, during a survey looking for pulsars near the Magellanic Clouds. The signal had been sitting in that data, unexamined, for 6 years. It lasted about 5 milliseconds. Its peak brightness was above 30 Janskys at 1.4 gigahertz, which was enough to saturate the telescope's digitizers, and it showed up in 4 of the instrument's 13 beams at once. The number that mattered was its dispersion measure. When a radio pulse travels through ionized gas, the lower frequencies arrive slightly later than the higher ones, and the size of that delay tells you how much gas the pulse crossed. This one had a delay about 10 times larger than the Milky Way could account for along that line of sight, which meant the pulse had crossed something far bigger than our galaxy. It had been traveling through the thin gas between galaxies for a very long time. Then came the repeaters, and they changed the problem entirely. Laura Spittler and colleagues published the first one in Nature in 2016. It had been found in Arecibo survey data, and then it was caught again, 10 more times, from the same position and with the same dispersion. That single fact ruled out one whole class of explanation. Whatever produces at least some of these cannot be a one-time catastrophe, because a star that explodes does not do it twice. The source was eventually pinned down to milliarc-second precision using an array of telescopes spread across continents. It sits in a dwarf galaxy with a persistent radio source right on top of it. Then one of them started keeping a calendar. The CHIME telescope in British Columbia reported in Nature in 2020 that one repeating source has a cycle of 16.35 days. Across 38 bursts recorded between September 2018 and February 2020, every single burst arrived inside a 5-day window of that cycle, and half of them inside a window of about 14 hours. The leading interpretation is that we are watching an orbit, two objects going around each other, with the bursts only escaping when the geometry is right. And then one of them kept time inside a single burst. In 2022, CHIME reported a burst lasting about 3 seconds, which is a wild outlier, containing 9 or more separate components, separated by a regular 216.8 milliseconds. That regularity was measured at 6.5 standard deviations. Something was oscillating, precisely, 5 times a second, in a burst that crossed the universe to reach us. That kind of clock points hard at a neutron star, and specifically at emission from inside a neutron star's magnetic field. The case largely closed on the 28th of April 2020, and it closed at home. On that night, an extremely bright millisecond radio burst arrived from a known magnetar inside our own galaxy, catalogued as SGR 1935 plus 2154. 2 instruments detected it independently and simultaneously, and an X-ray burst arrived alongside it. Its energy was only about 30 times below the faintest extragalactic burst on record, which is close enough that it plausibly belongs to the same population. That was the first fast radio burst ever tied to a known object of any kind. A magnetar is a neutron star with a magnetic field roughly 1,000 trillion times Earth's, and when its crust cracks, the energy has to go somewhere. The numbers now are large. The first CHIME catalogue, in 2021, held 536 bursts. The second, released in 2025, holds 4,539, recorded between July 2018 and September 2023, of which 981 come from 83 known repeating sources and 3,558 appear to be one-offs. CHIME picks up 2 or 3 a day. A 2026 analysis brings the repeater count to 80. The bottleneck is not detection. It is location. Of roughly 1,000 published bursts, only about 50 have an identified host galaxy. Everything else is a statistical entry in a table, a real event with no address. And one of the ones with an address is the reason this file is still open. The source catalogued as FRB 2220E sits inside a globular cluster in the galaxy M81, 2 parsecs from the cluster's center. Globular clusters are old. The stars in them finished forming billions of years ago, and nothing new has been born there since. A magnetar made the ordinary way by the collapse of a massive young star would have gone quiet long before. The standard story cannot apply there. The workarounds proposed involve a magnetar formed instead by the collapse of a white dwarf that accumulated too much mass, or by the merger of two compact objects. Both of those mean there is more than one way to build one of these things, which means there is probably more than one kind of source, and that the population we are looking at is not a single phenomenon at all. Meanwhile, and almost as a side effect, these bursts have become genuinely useful, and this is the quiet payoff of the entry. In 2023, a burst was traced to a galaxy at a redshift of 1.016, making it the most distant confirmed, with about 4 times the energy of any other on record. Its dispersion exceeded the standard prediction by a large margin, and its host turned out not to be a single galaxy, but a compact group of them. And in 2025, a team led by Liam Connor used a set of localized bursts to settle a problem that had been open for decades. Roughly 3/4 of the ordinary matter in the universe, not dark matter, ordinary atoms, had never been located. Astronomers could account for what is in stars and in galaxies, and the sums did not work. Using the dispersion of these bursts as a way of weighing everything they passed through, the team found it. About 76% of it is sitting in the thin gas between galaxies, about 15% is in the halos around them, and only about 1/4 of all the ordinary matter in the universe is bound inside a galaxy at all. That is a genuinely large result, and it came out of trying to explain something else entirely. There is a technosignature proposal in the literature, and it deserves a clear label. Manasvi Lingam and Avi Loeb published a paper in 2017 suggesting these bursts could be leakage from beams used to push enormous light sails between the stars. The paper's actual content is an engineering constraint calculation. For the numbers to work, the emitter would have to be roughly the diameter of a rocky planet, powered by the sunlight falling on an area about twice the size of Earth. Its one genuinely interesting feature is a coincidence. The optimal frequency for pushing such a sail sits close to the frequencies at which these bursts are observed. Loeb himself describes the work as speculative, and the magnetar evidence has moved the field decisively away from it. It stays in this list as an example of the process working, a hypothesis proposed, examined, and quietly set aside once better data arrived. So the honest position at number 15 is this. The magnetar model is confirmed for at least one burst. It is the leading explanation overall, and it is not a settled universal answer. The overwhelming majority of the 4,500 catalogued bursts have no known source, no host, and no distance. And the way that gets resolved is not by a single decisive observation. It is by collecting more of them for years, until the population itself starts to speak. Those bursts are strange because we cannot place them. The next sign is strange for the opposite reason. We have counted more than 6,000 of them, and the counting is what makes the case. Number 14, 6,000 worlds. We have come down from 20 to 14, and it is worth stopping for a moment to see how far the ground has already shifted. We began with an idea that no instrument could ever test. Then a catalogue of stars with a view of us. Then a single unrepeated signal and a residue of unresolved sightings, and one object that left before we could look at it properly, and a population of bursts we are still learning to place. Every one of those still waits on something. Number 14 does not wait. It has already happened, and it happened so gradually that most people missed the moment it became true. In 1995, Michel Mayor and Didier Queloz found a planet orbiting another sun-like star. It was a gas giant on a 4-day orbit, sitting far closer to its star than anything in our own system, and no theory had predicted it. They shared the Nobel Prize in Physics for it in 2019. Before that night, the number of confirmed planets around other stars was 0. Every conversation about life elsewhere was conducted without knowing whether there was anywhere for it to live. The Kepler spacecraft launched in March 2009 and turned a handful of detections into a census. On the 17th of September 2025, the confirmed count passed 6,000, and it has continued climbing since, by roughly 100 a month. Nearly half of the 1,000 confirmed since 2022 came from a single successor mission. Researchers quoted at that milestone expect 10,000 within a few years. The most famous of them is a good illustration of how slowly certainty actually arrives. Kepler 452b was announced on the 23rd of July 2015. About 1,400 light-years away in Cygnus, a radius about 1.63 times Earth's. An orbital period of 385 days, which was the closest match to our own year found up to that point, and which is what drove the coverage. The host star is the same spectral class as the Sun, but roughly 1.5 billion years older, which means it is brightening, and the planet may already be sliding into a runaway greenhouse. Earth's older cousin, as it was called at the time. Then it came apart. Fergal Mullally and colleagues published in the Astronomical Journal in 2018 under a title that says, "Everything. Kepler's Earth-like planets should not be confirmed without independent detection." Their simplest calculation gave only a 16% probability that the signal was a real transit on that star. Their most optimistic gave 92%, which is still far short of the 99.7% claimed at announcement. Their conclusion was that it should no longer be considered confirmed, and a follow-up using the final Kepler data release agreed. Then it came back. In 2025, a paper in the Proceedings of the National Academy of Sciences introduced a different statistical method, building null signal templates by shifting transit times by small random amounts, which gives each star its own false alarm probability rather than applying a general one. Rerunning all 47 previously proposed habitable zone Earth-like Kepler candidates, they found 29 with a false alarm probability under 1%. Kepler 452b is among their confirmations. In the same pass, they downgraded another famous candidate, Kepler 186f, assigning it a 20% chance of being a false alarm. So the honest position in 2026 is that the most famous Earth-like planet ever announced has been validated, unvalidated, and revalidated across 10 years and has never once been independently detected by any other technique. That is the underlying reason the argument can keep swinging. It is not a scandal. It is what statistics looks like at the very edge of an instrument's sensitivity. It is a question with no appointment, not because nothing could settle it, but because the observation that would settle it is beyond anything currently pointed at a star that faint at that distance. The number that actually matters is not a single planet. It is a rate and it is a range rather than a figure. Steve Bryson and colleagues published it in the Astronomical Journal in 2021. They asked how often a temperate rocky planet, between 0.5 and 1.5 times Earth's radius, in the zone where liquid water could sit on the surface, occurs around a star broadly like the Sun. Their answer runs from about 1/3 to about 6/10, with error bars wide enough that the honest reading is somewhere between 1 in 5 Sun-like stars and rather more than one each. Set that against a galaxy holding on the order of 100 to 400 billion stars. The arithmetic is the argument. It does not say anyone is there. It says the accommodation exists in enormous quantity, and that 30 years ago we did not know whether it existed at all. The confirmed roster of temperate rocky worlds is still short, and the names are worth having. There is a planet called TOY 700d, validated in 2020, about 1.19 times Earth's radius, sitting in the conservative habitable zone of a red dwarf 101 light-years away. Its neighbor, TOI 700e, announced in 2023, is about 95% of Earth's size on a 28-day orbit. And there is Proxima Centauri b, at least 1.07 Earth masses on an 11-day orbit, 4¼ light-years away, nearer than any other planet outside this system, and we will come back to it near the end of tonight. A running catalogue of potentially habitable worlds lists around 70 in total, of which a conservative sample of 29 are more likely to be genuinely rocky. And the shape of the population turned out to be a discovery in itself. Benjamin Fulton and colleagues found in 2017 that small planets come in two sizes with a gap between them. There is a peak around 1.3 times Earth's radius, a second peak around 2.4, and a deficit at about 1.8. That gap is thought to mark the size where stellar radiation, or a planet's own internal heat, strips its hydrogen envelope away and leaves a bare core behind, which produces the oddest fact in this entry. The two most common types of planet in the galaxy sit on either side of that gap, and neither of them exists in our own solar system. We have nothing between Earth and Neptune. Most stars do. Counting the worlds is one thing. The next sign is about a single property one of them may have, and it is the only property on this list that can only be measured in radio. Number 13. A planet with a magnetic field. Almost every temperate rocky planet we know about orbits a red dwarf. That is not because red dwarfs are special. It is because they are small and dim, which makes a planet crossing them easier to see, and because there are far more of them than there are stars like the Sun. It creates a problem. Red dwarfs are violent. They flare, they blast ultraviolet light, and their habitable zones sit so close in that a planet there is sitting inside a dense stellar wind. Over billions of years, that wind can strip an atmosphere away, molecule by molecule. The thing that stops it is a magnetic field. Earth has one, and it deflects the solar wind around us. Mars lost its global field roughly 4 billion years ago, and then lost most of its atmosphere, and those two facts are not a coincidence. So the question of whether the nearest habitable zone planets have any air at all may come down to whether they have a magnetic field. And here is the difficulty. Neither of the two techniques we use to study exoplanets can measure one. Watching starlight filter through an atmosphere tells you nothing about magnetism. Neither does direct imaging. There is exactly one channel that works, and it is radio. The first credible candidate arrived in April 2023. Sebastian Pineda and Jackie Villadsen published in Nature Astronomy on YZ Ceti, a red dwarf about 12 light-years away, observed with the Very Large Array between 2 and 4 gigahertz. They found repeated coherent radio bursts, strongly polarized, tightly organized radiation of the kind produced by a specific mechanism called the electron-cyclotron maser. It is the same mechanism that makes Jupiter one of the loudest radio sources in the sky. YZ Ceti has a compact family of terrestrial planets, and the innermost one goes round in about 2 days. 2 of the bursts occurred at similar points in that planet's orbit, which suggests the bursting becomes more likely when the planet sits in a particular place. Modeling of the system's magnetic environment showed the planet could plausibly supply the power. The mechanism is worth understanding because it is borrowed directly from our own solar system. Jupiter's moon Io plows through Jupiter's magnetic field, and the interaction sets up an enormous electrical current that flows down the field lines and lights up radio emission where they meet the planet. The exoplanet version is the same thing with the roles enlarged. The planet plows through the star's field, and the star's magnetic footpoints glow. For that to work, the planet has to be an obstacle to the field. It has to have one of its own. That is why this observation matters. It is an indirect measurement of something we cannot otherwise reach. And the star's slow rotation is what makes the reading credible, because a fast-spinning red dwarf produces bursts like these entirely on its own. There is a further elegance to the technique that is easy to miss. In this mechanism, electrons spiral along magnetic field lines, and the frequency at which they emit is set directly by the strength of the field they are spiraling in. So the frequency is not incidental. The frequency is the measurement. If you can catch the emission and read where in the spectrum it sits, you have weighed the magnetism. It is also worth remembering how the first example of this was found. In 1955, two researchers using an array in Maryland kept picking up bursts of radio noise they assumed were interference from a passing car or a faulty piece of equipment. It took them months to realize the noise was arriving on a schedule and that the schedule matched Jupiter. The loudest planetary radio source in the sky was discovered by people trying to work out what was wrong with their own instrument. The author's own caution is kept here because it belongs to the result. They state they cannot rule out ordinary stellar magnetic activity without knowing how often slowly rotating stars produce such bursts by themselves. This is the leading candidate. It is not a confirmed exoplanetary magnetic field. There was an earlier claim, and it is instructive to see what happened to it. Jake Turner and colleagues reported, from work in 2020, that the LOFAR array in Europe had picked up circularly polarized bursty emission from the Tau Bootis system, most plausibly from the hot Jupiter orbiting there. A follow-up published in 2024, using a newer French array, found nothing at all. Two readings survive. Either the original detection was an unrecognized instrumental effect, or the emission varies with time and the second search missed it. As of this year, it is not a confirmed detection. Which brings us to the state of the field, stated plainly. There are still no confirmed detections of radio emission from any exoplanet. A systematic survey of 140 planets with the Very Large Array, published in 2024, found none. What is changing is the method. In early 2026, a new analysis technique was applied to more than a year and a half of LOFAR sky survey data, generating something on the order of 200,000 dynamic spectra of isolated stars and planet hosts. Some of those signals show every characteristic expected from magnetic interaction between a star and a planet. The same technique applied to a French array produced a burst from another known planetary system. Those are candidates, not confirmations, and the people involved say so. The instrument that settles it is being built. The low-frequency half of the square-kilometer array is projected to be about 30 times more sensitive than LOFAR, and the published expectation is that it is very likely to detect exoplanetary radio signals once it is running. So, the honest description of number 13 is exploratory. Real methodological progress, one strong candidate 12 light-years away, and 0 confirmations. And a stake that is larger than the entry's size suggests, because whether the nearest temperate planets have atmospheres at all may hinge on a property that no telescope built so far can measure. A magnetic field would tell us a world can keep its atmosphere. The next sign is about what somebody might have put into one. Number 12, a gas that only a factory makes. The cleanest way to find another civilization may not involve a signal at all. It may involve their rubbish. A radio message requires that somebody chooses to transmit, chooses to aim at us, and chooses to keep doing it long enough for us to be listening when it arrives. Industrial pollution requires none of that. It requires only that somebody exists and has been busy. Chlorofluorocarbons are close to a perfect example. There is no known way to make them without a factory. On Earth, they are entirely industrial. They were invented in the 1920s for refrigerators and aerosols, and every molecule of them in our atmosphere was put there deliberately. They persist for decades to millennia, so they accumulate rather than dispersing. And they absorb infrared light strongly and distinctively in exactly the window an infrared telescope looks through. If you found them in the atmosphere of another planet, there would be no natural explanation to fall back on. Henry Lynn, Gonzalo González Abad, and Avi Loeb ran the first calculation in the Astrophysical Journal Letters in 2014. Their two target gases were the two easiest industrial products to see. Their answer, about 1.2 days of total telescope time to constrain the first, about 1.7 days for the second, down to a level roughly 10 times current terrestrial concentrations. Their choice of target is the clever part. They picked Earth-sized planets transiting white dwarfs. A white dwarf is itself roughly the size of Earth, so an Earth-sized planet passing in front of one blocks an enormous fraction of the disk, rather than a fraction of a percent. The atmospheric absorption becomes reachable in a way it never is around an ordinary star. Jacob Hack-Misra and colleagues extended the calculation to a real, nearby target in the Planetary Science Journal in March 2022, modeling two specific chlorofluorocarbons in the atmosphere of a temperate planet in the TRAPPIST-1 system. With an optimistic instrument noise floor, present-day Earth levels are detectable in about 100 hours of in-transit time. With a conservative noise floor, even 5 times Earth levels are not detectable in any amount of observing time at all. That contrast is the honest version of this entry. The physics works. Whether the measurement works depends entirely on the instrument. The family of candidate gases has grown since. A proposal published in 2023 added nitrogen trifluoride and sulfur hexafluoride, both of which are fully fluorinated and contain no carbon at all, which makes them even harder to produce by accident. The authors describe them as close to ideal technosignature gases. Both are used in industry here, one in manufacturing flat panel displays, the other as an insulator in electrical switchgear, which is a small reminder that the specific chemistry of a civilization's exhaust is likely to be strange and particular rather than generic. There is a second pollutant on the list, and it came out of an unlikely observation. Ravi Kopparapu and colleagues published in the Astrophysical Journal in February 2021 on nitrogen dioxide, the gas that produces the brown haze over cities, motivated in part by watching urban nitrogen dioxide levels collapse worldwide during the pandemic. Their headline figure, present-day Earth levels on a planet around a Sun-like star 10 parsecs away, would be detectable at 5 standard deviations in about 400 hours with a 15-meter space telescope. Two details make that more interesting than it first sounds. Nitrogen dioxide builds up more around cooler stars because there is less short-wavelength light to break it apart. And Earth's own nitrogen dioxide was about 3 times higher 40 years ago than it is today, before emissions controls. So the technique would find a slightly older version of us more easily than the current one. The authors also state their own limitation plainly, and it is kept here. Clouds and aerosols reduce the detectability and can mimic the feature. The 400-hour number is for a cloud-free planet. And then there is the strangest proposal of the set, which is to look for the lights. Thomas Beattie published it in monthly notices of the Royal Astronomical Society in 2022. He modeled a planet's night side illuminated by high-pressure sodium lamps reflecting off concrete, a spectrum that is measurably different from reflected starlight. For Proxima Centauri b, a 15-meter telescope working by direct imaging could detect city lights if about 0.6% of the surface were urbanized. Earth's actual figure is about 0.05%. So the technique works at about 12 times our own current level of development. Which is not a limitation exactly. It is a statement about how much room there is above us. All of this rests on one instrument that does not exist yet. The Habitable Worlds Observatory is designed to directly image Earth-like planets around Sun-like stars and take their spectra. A primary mirror 6 to 8 meters across, working from the ultraviolet through the near-infrared, with starlight suppression at the level of 1 part in 10 billion, which is the hard part, because that is the contrast between a star and a planet next to it. The target list is roughly 25 potentially habitable worlds. Its Technology Maturation Office was established in August 2024, and the first technology demonstrations were expected in the spring of this year. 7 companies hold 3-year study contracts. Launch is projected for the 2040s. And the funding is contested in the way these things usually are. The budget request for this year asked for $3.3 million for its technology development. The appropriations bill carried $150 million. There is a formal review at the end of this decade at which the whole project can be cancelled if the milestones are missed. This is not a guaranteed telescope. One more point belongs here because it applies to every search on this list and is almost never made. A non-detection is a result. If that observatory eventually looks at 25 nearby habitable worlds and finds no industrial chemistry in any of their atmospheres, that is not nothing. It sets a real upper limit on how many industrial civilizations exist within a certain distance of us, and it is the first such limit anybody will ever have measured rather than assumed. Which leaves number 12 where it sits. A method with no natural false positive, a set of published detection budgets that are entirely reasonable, and a hard dependency on an observatory that has to survive another 15 years of budget cycles before it flies. There is a quiet irony in it worth naming once. The clearest evidence a civilization could possibly leave behind is the evidence of its own industrial waste. That sign waits on a telescope nobody has finished. The next 4 wait on something harder, a spacecraft that has to physically arrive. Number 11, the ocean that keeps answering questions nobody asked. Enceladus is 500 kilometers across. It would fit inside the state of Arizona with room to spare. It is the 6th largest of Saturn's moons, and until 2005, it was a bright dot with nothing much to say for itself. Then Cassini found the plume. Water is venting continuously from the south pole of that moon through 4 roughly parallel fractures in the ice, each about 130 kilometers long. They were named for places in the Arabian Nights, Alexandria, Cairo, Baghdad, and Damascus, and everyone calls them the Tiger Stripes. The activity rises and falls with the orbit. As Enceladus moves around Saturn on an eccentric path, the fractures experience varying shear and varying pull, and the jets respond. The formation model is neat. As liquid water freezes beneath the shell, it expands, pressurizing the ice from below until it cracks, and tidal heating had already thinned the ice at the poles, which is why only one pole gave way. What that means, practically, is that a moon has been handing samples of its own hidden ocean out into space, for free, for as long as anyone has been watching. On the 28th of October 2015, Cassini flew straight through the curtain at 49 kilometers above the surface, with its mass spectrometer open. Picture it. 49 kilometers up, over a body 500 kilometers wide, moving fast enough that each individual ice grain becomes a small chemistry experiment the instant it strikes the detector. Below, 4 parallel cracks in white ice, each one longer than the length of England, venting into vacuum. There is no sound. The whole pass takes seconds. And the spacecraft doing it was designed, built, and launched before anyone knew the plume was there at all. Every instrument being used was repurposed on the fly by people who had planned a completely different mission. Here is what 4 locks opening in order looks like. The first is energy. Hunter Waite and colleagues published the composition in Science in 2017 from that dive. 96 to 99% water vapor, 0.3 to 0.8% carbon dioxide, 0.1 to 0.3% methane, 0.4 to 1.3% ammonia, and 0.4 to 1.4% molecular hydrogen. Hydrogen at that abundance is best explained by hot water reacting with rock at the bottom of the ocean. And hydrogen together with carbon dioxide is a chemical disequilibrium, which is another way of saying it is free energy sitting there unused. On Earth, that exact pairing is what methane-producing microbes live on. Every compound required for that metabolism is present in the plume. The second lock is the confirmation that the rock is hot. Traced through Saturn's outer ring, Cassini found silica nanoparticles, tiny grains of quartz, which only form when water and rock are in contact above about 90 degrees Celsius. That is not inference. That is a hydrothermal system at the base of the ocean with the products floating past a spacecraft. The salts are the third piece of the picture, and they settle a basic question. The plume carries sodium and potassium salts, which means it is coming from liquid water rather than from ice quietly sublimating. There is a sea down there, not just a frost. There is also a visible consequence of all this that is easy to overlook. The material Enceladus throws out does not simply disperse. It feeds Saturn's outermost ring, which means that Moon has been painting a ring around its own planet with the contents of its hidden ocean, continuously, for as long as it has been cracked. The ring was catalogued long before anybody knew where the material came from. The fourth lock is nutrient. Frank Postberg and colleagues reported in Nature in 2018 that the grains carry concentrated macromolecular organic material with molecular masses above 200 atomic mass units. Before that, only simple molecules mostly under 50 had been seen. And then, in June 2023, the same group published the one that mattered most, sodium phosphates, implying phosphate in that ocean at roughly 100 times the concentration found in Earth's oceans. Phosphorus is the element that most often limits life in our own seas. It is the reason fertilizer exists. Finding it in abundance closed the last gap in the list of elements that living chemistry requires. After that paper, Enceladus had all of them. In December 2023, a team led by Jonah Peter added hydrogen cyanide, which sits at the center of nearly every laboratory model of how life's chemistry begins, along with acetylene, propene, and ethane. Their second finding is arguably larger than the first. The plume shows far more varied and more oxidized chemistry than methane production alone would generate, which means substantially more chemical energy available down there than earlier models allowed. And then there was one remaining objection, which was quietly the most serious of all. Every organic detection up to that point came from grains in Saturn's outer ring, grains that had left the Moon years or centuries earlier and had been sitting in space being processed by radiation ever since. Perhaps the complex molecules were made out there, by radiation, and were never in the ocean at all. In October 2025, a team led by Nozer Khawaja and Frank Postberg published the answer in Nature Astronomy. They analyzed grains struck at nearly 18 kilometers a second, a speed high enough to fragment the molecules differently and expose pieces that had never been seen. They found aliphatic compounds, cyclic esters and alkenes, ethers, and tentatively compounds containing nitrogen and oxygen. The critical detail is which grains those were. They had left the moon minutes earlier. Not years. Minutes. Which means the complex organic chemistry is in the ocean itself and is not an artifact of anything that happened afterwards. The interior for completeness. A global ocean about 40 kilometers deep, beneath an ice shell averaging 20 to 25 kilometers, more than 30 at the equator and under 10 at the South Pole, in places only a few. Tidal heating models allow up to about 50 gigawatts of equilibrium heat production. The South Polar terrain radiates about 15, with roughly 5 along the stripes themselves. The mismatch between what the models produce and what the moon actually emits has never been resolved, and it is a genuine open problem rather than a rounding error. So here is where number 11 stands. Every element life requires, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, has been measured in seawater venting from a moon small enough to fit inside a single American state. There is liquid water. There is hot rock in contact with it. There is a chemical energy gradient. There is complex organic material, confirmed to be in the ocean and not made afterwards. Every box that could be ticked from a distance has been ticked. And nobody is going. There is no funded mission to Enceladus. The European Space Agency's committee for its 4th large-class mission identified it as the top target in 2024, prioritizing an actual landing near the Tiger Stripes plus an orbiter that samples the plume, and a study team has been working with a payload group since March 2025. The tentative profile is a launch around 2042, arriving in the early 2050s, timed so the South Pole is in constant sunlight when it gets there. On the American side, a concept called Enceladus Orbilander, orbit for about a year and a half, then land and work the surface for 2 more, was ranked the 2nd highest priority new flagship mission by the most recent Decadal survey. Second means it has not started. Its estimated cost is around $4.9 billion. The realistic answer, from either agency, is the early 2050s. That is the reason this entry sits at 11 and not lower, and it is a strange thing to have to say about the most complete case anybody has assembled. That ocean has everything it needs and nobody coming. The next world has a mission already funded, a launch date and a landing site chosen, and it will still take until the middle of the 2030s. Number 10. The moon with the wrong chemistry. There is exactly one other place in the solar system where liquid falls from the sky, collects into seas, and cuts channels into the ground on its way there. It is a moon of Saturn. It is larger than the planet Mercury, and the liquid is not water. Titan has the thickest atmosphere of any moon in the solar system, and it is thicker at the surface than Earth's. Surface pressure is about 1.45 bar, which is roughly 50% more than sea level here. Mean surface temperature is about 94 Kelvin, or minus 179 degrees Celsius. The air is about 95% nitrogen and 5% methane, and it extends about 600 kilometers upward, around 10 times the vertical extent of ours. If you stood there in a heated suit, the pressure would be comfortable, and the gravity would be low, and the light would be dim and orange, like a very late afternoon that never ends. What falls out of that sky is methane, and it falls in drops that are larger and slower than rain here, because the gravity is weak and the air is thick. It collects into seas near the poles, and Cassini's radar measured them. Kraken Mare is the largest, covering about 400,000 square kilometers, bigger than the Caspian. The radar measured it at least 300 meters deep near the center, and then got no return at all from the very deepest part, which means it is either too deep to sound or too absorptive to see through. Nobody knows how deep it goes. Ligea Mare was modeled at about 160 meters along a 300-kilometer track. Punga Mare's greatest measured depth is 110 meters. We have stood there once. The Huygens probe touched down on the 14th of January 2005 after a descent lasting 2 hours and 27 minutes through the haze. It kept transmitting from the surface for about 72 minutes until Cassini carried its relay antenna over the horizon and the link went quiet. It remains the most distant landing ever made by a spacecraft, and nothing planned will beat it. What it photographed was a flat plain scattered with rounded, pebble-sized lumps. Those lumps are water ice. At 94 Kelvin, water ice is as hard as rock and behaves like it. And they are rounded, which means something flowed over them for a long time. On Titan, the rock is ice and the water is fuel. Cassini made 127 close Titan flybys across 13 years. The last one, on the 21st of April 2017, was the pass that bent the spacecraft onto the trajectory that ended the mission. Underneath all of it, there is water after all. Luciano Yies and colleagues measured Titan's tides using Cassini's radio link in 2012. Saturn distorts the Moon's surface by more than 10 meters, which is far more give than a solid body would have. Yies's own summary was that the conclusion is almost inescapable. There is a hidden ocean at depth. Models put it up to about 250 kilometers deep beneath an ice shell around 50 kilometers thick, though other estimates in the same literature run to 500 or 700 kilometers. The depth is genuinely unsettled. The composition is inferred to be water salted with ammonia, which lowers its freezing point enough to keep it liquid. But the reason Titan is on this list is not the ocean. It is what is happening in the air. Sunlight and energetic particles break nitrogen and methane apart in the upper atmosphere, and the fragments recombine into progressively larger organic molecules. Those molecules eventually get heavy enough to fall, and they rain down as brown solids called tholins, which is what gives the Moon its color and what hid its surface from every telescope for a quarter of a century. Titan was a featureless orange ball until radar and infrared learned to see through it. Hydrogen cyanide is one of the important intermediates. It is produced while the haze particles are absent, and progressively consumed as they form and grow. And then there is vinyl cyanide, and a proposal that did not survive. Maureen Palmer and colleagues published the first definitive detection of vinyl cyanide in Titan's atmosphere in 2017, using archival ALMA data. It mattered because of an idea published 2 years earlier. James Stevenson, Jonathan Lunin, and Paulette Clancy had modeled what would happen if vinyl cyanide molecules assembled into a sheet in liquid methane. The answer was that they could form a stable sheet, and that the sheet could close into a hollow microscopic sphere, a container, functionally a cell membrane, for a world where the water-based membranes life uses here would be frozen solid. They called it an azotosome. It was one of the more genuinely imaginative pieces of chemistry anyone has published about another world. And in 2020, Martin Rahm and a colleague showed thermodynamically that such structures are unfavorable at Titan's temperatures, and concluded they cannot exist there. That is worth telling in full rather than leaving out, because a hypothesis proposed, tested and abandoned is the honest shape of this entire field, and it happens far more often than a hypothesis that survives. Which brings us to what is actually being sent. Dragonfly is confirmed, built by the Johns Hopkins Applied Physics Laboratory. The launch window runs from the 5th to the 25th of July 2028. Arrival is December 2034. The nominal surface mission is about 3.3 years. Total life cycle cost is $3.35 billion, which is roughly double the original proposal and more than 2 years later than the original schedule, a slip that NASA's own Inspector General criticized in a report published in September 2025. As of this year, structural testing is complete and full spacecraft integration has begun. And it is a rotorcraft. It will be the first aircraft to fly on any world other than Earth and Mars, and Titan is about the easiest place in the solar system to fly, because the air is thick and the gravity is weak. It lands in the Shangri-La dune fields, which are equatorial seas of organic sand, and then it hops. Over a series of flights, it works its way towards Selk Crater, an impact basin about 80 kilometers across. Selk is the target for a specific reason. An impact of that size would have melted water ice and mixed it, hot, with the surface organics, and that mixture, water plus organic material plus heat, is precisely the laboratory that produces amino acids. It carries 4 instruments. A mass spectrometer that vaporizes samples with a laser and looks for the molecular patterns that indicate prebiotic chemistry. A gamma ray and neutron spectrometer that reads surface composition without touching anything. A geophysics and meteorology package. And a camera suite. There is a pessimistic result that belongs here, and it should be given its full weight rather than tucked away. Catherine Nish and colleagues published in the journal Astrobiology in February 2024, modeling how much organic material from the surface actually makes it down into the ocean below via impact cratering. Converted into something you can hold, their answer is about 7,500 kilograms of glycine per year. Roughly the weight of one elephant, delivered annually into an ocean larger than all of Earth's. Their conclusion was that this is probably not enough to sustain anything living down there, which is a useful result rather than a disappointing one, because it redirects the question. If the ocean is not the place to look, then the surface is the dunes and the crater floors, where the chemistry is happening in the open and where something is going to land in December 2034. Titan's chemistry is strange because it runs on the wrong liquid. The next sign is strange because of a molecule that should not be in that atmosphere at all, and 5 years of argument have not settled whether it is really there. Number 9. The molecule nobody can confirm or kill. On the 14th of September 2020, a team led by Jane Greaves published a paper reporting a molecule called phosphine in the clouds of Venus. 6 years later, that result has neither been confirmed nor killed, and the story of why is the most instructive thing on this list about how a claim actually behaves under sustained scrutiny. Underneath it sits a second mystery, much older and far less discussed, and by some measures more important. We will come to that. Start with the claim. The team found an absorption line near 266.9 gigahertz, the 1.123 millimeter transition of phosphine, first in 2017 data from the James Clerk Maxwell Telescope in Hawaii, and then recovered it in 2019 data from ALMA in Chile. The inferred abundance was about 20 parts per billion, at the cloud deck around 55 kilometers above the surface. Why anyone cared takes one sentence. On a rocky, oxidizing planet, phosphorus should end up locked into phosphates. It should not be floating around as phosphine. Phosphine does form without life inside Jupiter and Saturn, but only under pressures and temperatures that Venus does not have anywhere. Then came 6 years of argument, and it is worth walking through, because each step is a real piece of science rather than a squabble. Venus is an unusually bright and awkward target at millimeter wavelengths, which makes calibration hard. Staff at ALMA subsequently found a ripple in the calibration, recalibrated the data, and re-uploaded a corrected version to the public archive. Ignas Snellen and colleagues reanalyzed and found no statistically significant detection, arguing that the very flexible polynomial used to fit the baseline could manufacture a feature that was not there. Geronimo Villanueva and colleagues published in Nature Astronomy in 2021 under the title "No Evidence of Phosphine in the Atmosphere of Venus from Independent Analyses." And a third group pointed out that sulfur dioxide has a line at a nearby frequency, and Venus has enormous amounts of sulfur dioxide. The original team answered in monthly notices of the Royal Astronomical Society in 2022. After the observatory's own recalibration, they recovered the feature using several independent reduction methods and estimated that sulfur dioxide accounts for no more than about 10% of the signal in the first dataset and under 2% in the cleaner part of the second. Their revised abundance came down sharply, a detection at about 5 standard deviations, with a local peak of 5 to 10 parts per billion and a planet-wide average of roughly 1 to 4. Far below the original 20. Where it stands now needs to be said carefully, because this is a case where enthusiasm and rigor pull in opposite directions. There is a monitoring program running on the James Clerk Maxwell telescope, awarded 200 observing hours, of which about 100 have been used. Its first campaign alone produced roughly 140 times as much data as the original Discovery dataset. A different analysis method recovered narrow phosphine lines and also lines of heavy water. An experimental reduction additionally recovered broad wings in the signal, which, if they really belong to phosphine, would imply about 300 parts per billion, near 55 kilometers, an order of magnitude above every earlier figure and correspondingly disputed. And the limitations are stated by the researchers themselves, which is the honest part. The follow-up work is not fully independent. The teams and the analyses overlap heavily with the original. Much of the processing is unfinished, and reflections inside the telescope system produce baseline ripples whose amplitudes are larger than the absorption lines being looked for. 3 separate questions get collapsed into one in almost every account, and separating them is the single most useful thing anyone can do here. Is the absorption feature real? Is phosphine the molecule producing it? And if phosphine is there, is anything alive making it? Those have different evidence behind them, and only the first is anywhere close to settled. On the chemistry, a review led by William Baines in 2024 examined volcanism, lightning, meteorites, gas phase reactions and photochemistry, and found no demonstrated mechanism that sustains the claimed amounts, while flagging photochemistry on cloud particles as an open possibility that needs laboratory work. That phrase, "no known process," is a statement about the limits of current models. It is not a proof that no process exists. There is a newer claim alongside it. In July 2024, at a national astronomy meeting in the United Kingdom, Greaves and her team announced a tentative detection of ammonia in Venus's atmosphere, using 2 telescopes together. It was presented at a conference rather than published, and it should carry that label. Its significance is mechanistic rather than rhetorical. Ammonia would neutralize the sulfuric acid droplets in those clouds, which is exactly what anything living in them would need to do to survive. And there is an odd piece of archival support. Rakesh Mogul and colleagues went back to data from a mass spectrometer aboard a probe that descended into Venus's atmosphere in December 1978. The original analysis had concentrated on the abundant species and paid little attention to trace chemistry. The re-examination of the lower and middle cloud data found signals consistent with phosphine, along with hydrogen sulfide, nitrous and nitric acid, hydrogen cyanide, and possibly ammonia. It is inference from unresolved peaks in 40-year-old data rather than a clean detection. But it was taken in place by an instrument inside the clouds, 42 years before anybody made the telescope claim. Now the older mystery, which almost nobody talks about, and which is, in a strict sense, larger. Something in Venus's clouds absorbs strongly between roughly 320 and 400 nanometers, the near ultraviolet. It was first noticed in the 1920s in work by Frank Ross and William Wright, which is why photographs of Venus taken in ultraviolet light show dark swirls and bands that are invisible to the eye. Here is the figure that matters. That unidentified substance captures more than half of all the solar energy Venus absorbs. More than half. It is not a curiosity in the corner of the spectrum. It drives the planet's entire energy balance, and it is bound up with the super-rotation of the atmosphere, which travels around the planet roughly 60 times faster than the planet itself turns. And after about 100 years, nobody can name it. No proposed candidate satisfies every observational constraint. The candidates are real, and each one partly works. Ferric chloride, where about 1% by weight, dissolved in the smallest sulfuric acid droplets, reproduces the absorption, with laboratory measurements under Venusian conditions published in 2025. Elemental sulfur in ring-shaped molecules, mostly the 8-atom form, with a few percent of smaller ones. Disulfur dioxide, which has been characterized in the laboratory and confirmed as a contributor, but is not sufficient by itself. Products of electrical breakdown of sulfur dioxide proposed last year. A biological hypothesis gets raised occasionally, because the absorber's spectrum resembles that of some terrestrial pigments, and there is no supporting evidence for it whatsoever. One more thing about those clouds is worth knowing before we leave. The layer between about 48 and 60 kilometers above the surface of Venus is the only place in the solar system, outside Earth, where the temperature and the pressure are both close to what you would find standing outside on a warm day here. Around 30 degrees Celsius. Roughly 1 atmosphere. That coincidence is the reason anyone has ever taken the idea of life on Venus seriously at all. The problem is what those comfortable conditions are made of. The droplets are concentrated sulfuric acid, and the amount of biologically available water in them is extraordinarily low. Low enough that it remains an unsolved objection even at benign temperature and pressure. Making phosphine and sustaining a cell are two entirely separate problems, and only the first one is under discussion. So when do we find out? Rocket Lab and MIT have built a small private probe, the first private mission to another planet, carrying a single instrument to look for organic molecules in the cloud droplets during roughly 5 minutes of descent. NASA's Da Vinci descent probe is a 2030s mission. A radar orbiter called Veritas launches no earlier than 2031 after budget delays. The European Envision orbiter launches in 2031, which produces the neatest irony in this entry. 6 years of argument, hundreds of telescope hours, a dozen papers and several bruised reputations, and a single descent probe carrying the right instrument would end the phosphine question in about 5 minutes of falling. Venus needs a probe that has not launched. The next sign is riding on a spacecraft that is already halfway there. Number 8. The ocean under the ice and the date it gets opened. The 11th of April, 2030. That is the reason this entry outranks the 4 above it. Not because the evidence is better. The evidence at Enceladus is arguably more complete. Because there is a date. Europa is about the size of our moon, 3,122 kilometers across, and it holds more water than Earth does. The ocean beneath its ice is estimated at 60 to 150 kilometers deep. Earth's oceans hold about 1.4 billion cubic kilometers of water. Europa's is estimated at around 3 billion. More than twice all the surface water on this planet, on a body you could drop into the Pacific. How we know is one of the more elegant pieces of physics in planetary science, and it is worth slowing down for. Jupiter's magnetic field is tilted relative to its rotation axis. So as Jupiter spins, the field at Europa's position sweeps back and forth rather than sitting still. If there is a layer of electrically conducting material inside the moon, that changing field will drive currents in it, and those currents will generate a magnetic field of their own, one that points in whatever direction the driving field demands, moment by moment. Krishan Khurana, Margaret Kivelson and colleagues reported the perturbations in Nature in 1998 from the Galileo spacecraft's magnetometer. The decisive test came on the 3rd of January 2000, on a pass far to the south of Jupiter's magnetic equator, where the driving field points inward rather than outward. Europa's measured field flipped with it. A permanent internal magnet cannot do that. Its poles are its poles. Only an induced field can reverse, and to induce a field you need a conductor, which, at those temperatures and in that setting, means salty liquid water in a global layer. How thick the ice above it is was one of the longest-running arguments in the field. Estimates ran from under a kilometer, which would allow surface material and ocean water to exchange more or less directly, to tens of kilometers, which would not. The two possibilities imply completely different worlds. It was settled recently, and not in the direction anyone was hoping for. Using microwave radiometer data from Juno's flyby of Europa on the 29th of September 2022, closest approach about 360 kilometers, covering roughly half the surface, a team measured subsurface temperature against depth and derived an average shell thickness of about 29 kilometers in the region observed. It was published in Nature Astronomy in December 2025. The project scientist's caveat belongs with the number. That figure describes the cold, rigid outer layer. If there is also a warmer, slowly churning layer beneath it, which is possible, the total is thicker still. It is the first measurement capable of telling the thin shell and thick shell models apart, and it favors thick, which means a long and slow path for anything on the surface to reach the water. There is a second clue on the surface itself, and it was noticed long before the magnetometer result. Europa has the youngest surface in the outer solar system, estimated at only 40 to 90 million years old, which means something has resurfaced it since the dinosaurs were alive. It is also among the smoothest bodies known, with almost no craters and almost no mountains. Both of those facts were what first made people suspect there was liquid underneath, long before anyone could prove it. The plumes are the contested part of this story, and they stay contested here. Lorenz Roth and colleagues reported in 2014 that Hubble had seen excess hydrogen and oxygen emission up to about 200 kilometers above the southwestern edge of the disk. William Sparks and colleagues reported ultraviolet shadowing at the limb in 2016, and a repeat at the same location in 2017, close to an unusually warm patch of surface. And Xianjie Jia and colleagues went back to Galileo data from a flyby on the 16th of December 1997 and found a rotation of the magnetic field and a spike in plasma waves consistent with the spacecraft having flown straight through a plume at about 400 kilometers altitude. That is the only measurement ever made from inside one, and it was found 21 years after the data was taken. Against all of that, Sophia, ALMA, the Subaru telescope, and the James Webb Space Telescope have all searched and found nothing. One of the web papers has the phrase, "no detection of plume activity" in its own title. Unlike Enceladus, Europa's plumes are not confirmed as persistent, and the honest reading is that they are occasional at best. What Webb did find, in September 23, matters more anyway. Two papers in Science mapped carbon dioxide ice across the surface and found it heavily concentrated in a region called Terra Regio, about 1,800 square kilometers of young, broken-up terrain, and the same region where Hubble had previously found salt that appears to have come from the ocean. The conclusion drawn was that the carbon most likely originates in the internal ocean, which is a bigger statement than it sounds. It means the ocean contains carbon, and it means material is crossing the ice shell, even if slowly. A follow-up in March 2026 extended that mapping into other resurfaced areas and strengthened the reading. One number went the wrong way. Juno's plasma instrument measured the rate at which radiation splits Europa's surface ice and frees oxygen, publishing in March 2024. The answer is about 12 kilograms per second. Earlier estimates had run from a few kilograms to more than 1,000. 12 is at the very bottom of that range, which means considerably less oxidant working its way down to the ocean than the optimistic models had assumed. And now, the spacecraft. Europa Clipper launched on the 14th of October 2024 from Kennedy Space Center. It is the largest spacecraft NASA has ever built for a planetary mission, and it cost about $5.2 billion. It flew past Mars on the 1st of March 2025 at 884 kilometers, using the encounter to calibrate its thermal imager and its radar against a planet whose properties are already known. Its Earth flyby is on the 3rd of December this year, at around 3,000 kilometers. That pass is not just for speed. It provides the only opportunity after launch to calibrate the magnetometer against a magnetic field whose strength is precisely known, which matters enormously because the magnetometer is the instrument that will measure the ocean. Jupiter orbit insertion is the 11th of April 2030. That date was fixed before launch because the entire multi-year tour was designed around it. A burn of about 6 hours, preceded roughly 12 hours earlier by a flyby of Ganymede at 200 kilometers, used to help slow the spacecraft down. Then, 49 science flybys of Europa, plus 7 of Ganymede and 9 of Callisto, used to shape the trajectory, running through 2034. The detail most people get wrong is why it orbits Jupiter instead of Europa. Europa sits inside one of the most intense radiation belts in the solar system. A spacecraft in orbit around the Moon would be cooked within months. So Clipper loops out into calm space between passes, dips briefly into the radiation each time, and gives its shielded electronics long stretches to recover in between. 49 short exposures instead of one continuous one. It carries 9 instruments, including an ice-penetrating radar, a mass spectrometer, a dust analyzer that can sample ocean-derived material blasted off the surface by micrometeorites without needing a plume at all, a boom-mounted magnetometer, and a thermal imager. And at the end, deliberately, it will be steered into Ganymede in about September 2034, so that nothing from Earth is left in orbit near a world we might want to sample later. One honest limit before we move on. Clipper is not a life detection mission. It is a habitability mission. It is designed to establish whether that ocean could support life, not whether it does. Even in 2030, the answer that comes back will be about conditions rather than occupants. That ocean gets its spacecraft in 2030. The next sign already has its sample, sealed, catalogued, and sitting on the ground, 400 million kilometers away. Number 7. The rock in the tube. This entry sits out of order, and it is better to say so at the start than to pretend otherwise. The rule for this list is how soon we find out. By that rule, a sample that has already been drilled, already been sealed, already been catalogued, and is already sitting on solid ground should be at or very near number 1. There is nothing left to find. The finding has happened. It is at number 7 because there is currently no funded way to bring it home. To understand why the standard of proof is now so high, we have to go back 40 years, to a piece of ice in Antarctica. On the 27th of December 1984, a meteorite hunting team working the Allen Hills picked up a greenish rock about the size of a potato. The person who found it was Roberta Score, who later ran the Antarctic Meteorite Laboratory at Johnson Space Center. It was misclassified at first and only identified as Martian in the early 1990s. Its crystallization age is about 4.09 billion years, which makes it one of the oldest Martian rocks anybody has ever held. On the 7th of August 1996, David McKay and colleagues published a paper in Science claiming 4 separate lines of evidence for past biological activity inside it. Carbonate globules in an igneous rock, which means water had been there. Organic molecules on fresh fracture surfaces. Crystals of magnetite and iron sulfide that closely resembled the ones made by magnetic bacteria on Earth. And elongated ovoid structures, 20 to 100 nanometers across, described as possible fossils. The same day, the President of the United States stood on the south lawn of the White House and called it potentially one of the most stunning insights into our universe that science has ever uncovered. In the same statement, he said it must be confirmed by other scientists and would continue to be reviewed, examined, and scrutinized. Both halves of that sentence turned out to matter, and only the first half was widely quoted. It was scrutinized. It did not survive. On size, the ovoid structures are below the roughly 200 nanometer floor, generally regarded as the smallest volume that can contain the machinery a cell needs. Many are now read as etching features or as texture from the metal coating used to prepare samples for electron microscopy. On the magnetite, a team led by David Golden published in the Proceedings of the National Academy of Sciences in 2002, showing that the same elongated crystals could be produced with no life involved, simply by heating iron-rich carbonate until it decomposed. On the organics, the hydrocarbons are not diagnostic of anything and are consistent with ordinary terrestrial material seeping in during the 13,000 years the rock sat in Antarctic ice. The last plank came out in January 2022. Andrew Steele and colleagues published in Science, showing complex organic material sitting alongside nanoscale magnetite in mineral assemblages formed when water reacted with rock roughly 4 billion years ago. Abiotic organic chemistry operated on early Mars. That is not a defeat. It is a different discovery and a real one. It just is not the one that was announced on a lawn. Which brings us to the rock that is actually in a tube. Between the 21st and 23rd of July 2024, the Perseverance rover was working the edge of Neretva Vallis, an ancient river valley about 400 meters wide that once fed a lake in Jezero crater. It came across an arrowhead-shaped outcrop about 1 meter long and 0.6 of a meter wide. The team named it Shayava Falls. It is a mudstone of clay and silt, rich in organic carbon, sulfur, oxidized iron, and phosphorus. Its surface carries millimeter-scale spots the team called poppy seeds, and larger ones they called leopard spots. Those are reaction fronts, the chemical signature left behind when something moved through a rock and changed it. 2 instruments identified what sits in those fronts. Vivianite, which is a hydrated iron phosphate. and greigite, which is an iron sulfide, both of them in close association with organic carbon. On Earth, that specific combination is the product of electron transfer reactions between sediment and organic matter. It is, precisely, the chemistry that microbes use to extract energy from mud. The setting matters as much as the chemistry. Jezero was a lake, and Neretva Vallis was the river that fed it, and the outcrop sits on what was once a riverbank. That is exactly where a geologist on Earth would go looking. Slow water, fine sediment, organic material settling out of it, the conditions under which a record gets written rather than erased. There is one more detail about those rocks that quietly overturned an assumption. They are among the youngest sedimentary units Perseverance has studied. The expectation going in had been that any biosignature would be found in the very oldest material, because the oldest material is closest to when Mars was warm and wet. This one is not. Which means the search area is larger than anybody had planned for. The core drilled out of it is called Sapphire Canyon. Joel Hurowitz and colleagues published the analysis in Nature on the 10th of September 2025. The wording NASA used was chosen carefully, and it should be reproduced carefully. A potential biosignature, defined by them as a substance or structure that might have a biological origin, but requires more data or further study before a conclusion can be reached. The project scientists' line is the one to keep. While abiotic explanations for what we see at Bright Angel are less likely given the paper's findings, we cannot rule them out. And the reason they are less likely is specific rather than rhetorical. The non-biological routes that would produce the same minerals require either sustained high temperatures or strongly acidic conditions. Those rocks show no evidence of either. Whatever happened there happened cold. There is a formal scale for this, running 7 steps from a possible signal to independent confirmation. This finding is at step 1. Getting past it means ruling out contamination, establishing biological plausibility, ruling out the abiotic routes properly, finding independent signals, and then having somebody else confirm it. Every one of those steps needs laboratory instruments that will not fit on a rover and cannot be flown to Mars. So the sample has to come here. In September 2023, an independent review board found that the existing Mars sample return architecture would cost between $8 and $11 billion and would not return anything before 2040, a decade past its own target. In April 2024, NASA asked industry for cheaper and faster designs. On the 7th of January 2025, it announced 2 candidate approaches, a larger version of the Sky Crane system that landed the rovers at 6.6 to 7.7 billion, or a commercial heavy lander at 5.8 to 7.1 billion. Earliest return between 2035 and 2039, with about $300 million a year needed simply to keep development alive. In May 2025, the budget request proposed cancelling the program outright. House appropriators earmarked $300 million to continue it. The Senate report did not address it. And the joint appropriation released on the 5th of January this year largely rejected the broader science cuts, but agreed not to fund the existing architecture. At a briefing in Paris on the 8th of January, the European Space Agency's Director General said that, at least according to today's plans, the mission will not go ahead and that Europe is evaluating its contribution. The agency's exploration director added that Europe cannot afford a full sample return mission on its own, and that the orbiter Europe had been building to carry the samples back may be repurposed for something else entirely. As of September 2025, Perseverance had collected 27 rock cores since landing on the 18th of February 2021. It carries 38 sample tubes and 5 witness tubes, the witness tubes being ones that were opened on Mars and sealed again without sampling anything, purely so that any contamination carried from Earth can be recognized later. Somebody thought about that in advance, years in advance, which tells you what kind of care went into this. And over 5 weeks, starting on the 21st of December 2022, the rover laid out 10 sealed titanium tubes in a zigzag on flat ground at a place called Three Forks. A backup cache, in case the rover itself could not deliver them. Stand there for a moment. It is a flat patch of Martian ground, chosen because it is flat and because it can be found again easily from orbit. 10 metal tubes lie on the dust in a deliberate pattern, each about the size of a cigar, each sealed, each catalogued, each holding a few grams of another planet. There is no wind strong enough to move them. There is nothing that will ever cover them over. The light shifts from pink to grey and back again with the seasons, and the tubes do not change. They will still be lying there in 100 years. They will still be lying there in 1,000. Somewhere over the crater rim, the rover that put them down is still working, still driving, still drilling. And the thing missing from that picture is not a machine, and not a technology, and not a piece of physics we have yet to work out. It is a decision made on a different planet, about a budget. Nobody went back to look. At number 18, that phrase meant the opposite. Everyone went back to look at the wow signal, roughly 50 separate times across half a century, and there was simply nothing there to find. Here there is something to look at. It has been drilled, sealed, photographed, published, and set down on the ground where it can be collected. That sample is waiting for a ride. The next sign is about a gas in the same planet's air, and the argument about it is happening right now, in print, this year. Number 6. The gas that should not last. 2 spacecraft are at the same planet. One of them keeps finding a gas. The other one, which is about 1,000 times more sensitive, has never seen it once in 8 years. Neither team has backed down. That argument is happening in print right now, this year, which is why it sits at number 6. Start with why the gas matters at all, because the reasoning is short and it is what makes the whole thing interesting. Methane in the Martian atmosphere is destroyed by sunlight on a timescale of roughly 300 to 400 years. The atmosphere itself mixes globally in a matter of months. 2 consequences follow immediately. Any methane present has to have been produced recently. There is no ancient reservoir sitting in the air, because it would have been gone long ago. And it ought to be spread evenly everywhere, which makes localized spikes physically strange. On Earth, more than 90% of atmospheric methane is made by living things. Now the measurements. The Curiosity rover carries a tunable laser spectrometer that draws Martian air directly into a chamber and measures what is in it. It has been doing this in Gale Crater since 2012. Christopher Webster and colleagues published 5 Earth years of data in Science in 2018, reporting a repeatable seasonal cycle in the background level, running between about 1/4 and 2/3 of a part per billion, averaging just over 4/10, and peaking in late northern summer. Then there are the spikes. The first, on the 15th of June 2013, at about 5.8 parts per billion. An elevated background of around 7 over a 60-sol window in the months that followed. And then, on the 18th of June 2019, about 21 parts per billion, the largest value in the entire mission. A rapid follow-up experiment that same weekend measured under 1. Whatever it was had dispersed within days. Meanwhile, in orbit, the ExoMars Trace Gas Orbiter has been looking for the same molecule using a completely different geometry. Rather than sampling the air where it sits, it watches sunlight pass sideways through the atmosphere as the sun sets behind the planet. That gives it a path length through the air of hundreds of kilometers instead of a few centimeters, which makes it roughly 1,000 times more sensitive than the instrument on the ground. Oleg Koroblev and colleagues published its first results in Nature on the 25th of April 2019. Across both hemispheres and a wide range of latitudes, no methane, with an upper limit of about 0.05 of a part per billion. That ceiling sits an order of magnitude below the rover's own claimed background. 8 years on, the orbiter has still detected nothing. And both European orbiters flew over Gale crater at similar times to the 2019 spike and saw nothing at all. That is the sharpest possible form of the contradiction. Same planet, same week, same patch of ground. 3 resolutions have been proposed, and they are genuinely different from one another. The first says, the methane never leaves the ground. Webster and colleagues published in Astronomy and Astrophysics in 2021, under the title Day-Night Differences in Mars Methane, suggest nighttime containment at Gale crater. The rover's measurements had historically almost all been taken at night. When the team ran daytime measurements in the same season, they got essentially nothing, 0.05 of a part per billion, against a nighttime background of about 0.5 a part per billion. The mechanism proposed is straightforward. Methane seeps slowly out of the ground at a low, steady rate. At night, the atmosphere near the surface collapses into a thin, stable layer, and the gas is trapped inside it at concentrations the instrument can find. By day, convection mixes that same amount of gas up into a column hundreds of times deeper, and it falls below detection. That reconciles a local, near-surface signal with a global column of nothing, because the amount involved is genuinely tiny. A related idea is barometric pumping. Pressure changes, physically drawing gas out of the pore space in the soil, which was modeled in detail in 2024. The second resolution says the ground is sealed and the seal breaks. A team at Goddard, led by Alexander Pavlov, published work in 2024, announced that April. They took simulated Martian permafrost containing perchlorate salts, cycled it through Mars temperatures and pressures, and injected neon as a stand-in for methane. A hard salt seal formed within 3 to 13 days, but only in samples containing 5 to 10% perchlorate. Warming sublimates the salty ice, cracks the seal, and releases whatever was trapped in a burst. The authors flag their own problem honestly. 5 to 10% perchlorate is far higher than the concentrations Curiosity has actually measured in Gale. The mechanism works in the laboratory. Whether it works on the planet is another question. The third resolution is the most uncomfortable, and it is the newest. Sébastien Viscardi and colleagues at the Royal Belgian Institute for Space Aeronomy published in the Journal of Geophysical Research in May 2025, under the title Questioning the Reliability of Methane Detections on Mars by the Curiosity rover. Reanalyzing the published spectrometer data, they found evidence of a leak into the instrument's four-optics chamber, before launch and during cruise, which raised its pressure by about 76 millibars and filled it with terrestrial air containing an estimated 10 parts per million of methane. They found methane abundances inside the four-optics 3 to 4 orders of magnitude higher than the values being reported from the sample cell, along with internal pressures that varied unexpectedly and rapidly. Their conclusion is that the detections may be instrumental rather than Martian. They also proposed a specific experiment the rover could run to discriminate between an internal source and the actual atmosphere. The rover team has not conceded the point, and the claim is itself contested. But it means that anybody reporting Curiosity's methane spikes as settled Martian fact in 2026 is reporting them wrong, and this list will not do that. There is a further limitation that applies no matter who wins, and it is worth understanding because it constrains the whole question. Suppose the methane is real. 3 sources could produce it. Methane-producing archaea living in a subsurface aquifer. Serpentinization, which is water reacting with olivine and pyroxene to make hydrogen, which then reduces carbon dioxide to methane, with no life involved at any point. Or ancient methane hydrates in the frozen ground, made long ago by either route, destabilizing and venting now. Telling those 3 apart requires measuring carbon and hydrogen isotope ratios, and the ratios of methane to ethane and propane. Life prefers lighter isotopes and leaves a measurable fingerprint. But those measurements need abundances far higher than parts per billion, and the instrument on Mars cannot make them. Which leaves the older detections and a brief and honest word about them. A global average of 10 parts per billion was reported from Mars Express in 2004. A similar figure was reported from the ground the same year. Plumes up to 45 parts per billion were reported in 2009. And in 2019, a European orbiter reported about 15 over Gale on the 16th of June 2013, one day after the rover's first spike, and the only apparent independent corroboration anybody has. All of those are contested, on instrument sensitivity, on interference from carbon dioxide in the same wavelength band, and on the difficulty of subtracting Earth's own atmospheric methane in the ground-based cases. The orbiter's current ceiling sits 200 times below that 10 parts per billion figure. They cannot both be right. So for 13 years, the strongest chemical hint of something alive on Mars has been a gas that one machine keeps finding, and another machine, 1,000 times more sensitive, has never once seen. The people who built both machines are still arguing about it, politely, in journals, this year. And the hardest part of finding life elsewhere may turn out to be trusting your own equipment. That argument is happening at a planet we can drive on. The next one is happening 124 light-years away, and for about a year, it was the biggest story in the field. Number 5. The gas that was announced, and then was not. In April 2025, a team at Cambridge announced what was widely reported as the strongest evidence yet for life. Within about 18 months, independent groups working on the same data had taken it apart. That is why this entry is at number 5. Not because the claim survived, because it was tested quickly and thoroughly, and the correction is the content. The planet is called K218b. It was found in data from the Kepler spacecraft's extended mission and announced in 2015. It orbits a red dwarf 124 light-years away in the constellation Leo. Its radius is about 2.6 times Earth's. Its mass is about 8.6 times Earth's. It goes round every 32.9 days, and it sits in its star's habitable zone. That size puts it in an awkward and very common category. Too large to be a rocky planet like ours. Too small to be a proper ice giant like Neptune. It is the most common kind of planet in the galaxy, and there is no example of it anywhere in our solar system. The first interesting result came in 2023. Niku Madhusudan and colleagues published observations from the James Webb Space Telescope detecting methane and carbon dioxide in the atmosphere, and, importantly, not detecting ammonia or carbon monoxide. The missing ammonia was the argument. In a deep hydrogen envelope, ammonia should be abundant. Its absence suggests something is removing it. A liquid water ocean underneath a thin hydrogen atmosphere would do exactly that, because ammonia dissolves readily in water. They gave the class of planet a name, Hycean, for hydrogen and ocean. Dimethyl sulfide appeared in that first dataset only as a tentative hint, below 3 standard deviations, and the team said so. Then came April 2025, and the numbers are worth having exactly. Using the mid-infrared instrument on Webb between roughly 6 and 12 microns, the team reported that the spectrum was inconsistent with a featureless model at 3.4 standard deviations. Dimethyl sulfide and a related molecule were jointly favored at 3.2. Dimethyl sulfide alone came in at 2.9. The convention in this field for a claim of this weight is 5 standard deviations, roughly a 1 in 3.5 million chance of the result being an accident of noise. 3 sigma is closer to 1 in 300. Every number in that paper was below the bar, and the paper said so. Why anybody cared is simple. On Earth, dimethyl sulfide is produced overwhelmingly by marine phytoplankton as a breakdown product of another compound they make. Here, it has no significant known non-biological source. That is what made it interesting, and that is precisely what stopped being true. The claim came apart from 4 directions at once. The first was reanalysis. A team led by Schmidt re-reduced the near-infrared data and confirmed methane at about 4 standard deviations, but found no statistically significant evidence for carbon dioxide or for dimethyl sulfide. Raphael Luque and colleagues published in Astronomy and Astrophysics under the title "Insufficient Evidence for These Molecules in the Atmosphere of K218b." When the mid-infrared and near-infrared data are analyzed together, the detection does not hold. Lewis Wellbanks and colleagues ran what is called an agnostic retrieval, which means asking the data what is in it without telling the software what to look for. It could not robustly constrain any biosignature gas. And a further paper in the Astronomical Journal carried the title K218b does not meet the standards of evidence for life. The second direction was more decisive, and it did not involve that planet at all. Abiotic dimethyl sulfide turned out to exist. Miguel Sanz-Novo and colleagues published evidence for it in cometary material from Comet 67P using data from the Rosetta mission in 2024. And then in 2025, they reported the first detection of dimethyl sulfide in the interstellar medium, in a molecular cloud near the center of the galaxy, where the temperature is close to absolute zero and nothing whatsoever is alive. The ratio of dimethyl sulfide to methanol in that cloud came out remarkably close to the ratio measured in the comet. The molecule's status as a clean biosignature did not survive that. It is not that the earlier reasoning was careless. It is that the universe turned out to have a route nobody had found yet. The third direction was more data. A program led by Renyu Hu, with Madhusudan among the co-authors, took 4 new transits between January 2024 and January 2025. Methane and carbon dioxide came through robustly. No detectable water, ammonia, or carbon monoxide. And dimethyl sulfide, along with 2 related molecules, came in below 3 standard deviations. Below 2, in fact, unless a strong haze model is imposed on the fit. The same paper's photochemical modeling showed that dimethyl sulfide can form without life in a massive, metal-rich hydrogen atmosphere. The fourth direction is the quietest and possibly the most damaging. A study published this year measured new laboratory infrared opacities for dimethyl sulfide and updated the opacities for ethane, including weak bands that had previously been left out of the models. Its conclusion, close to verbatim, is that the results support an ordinary sub-Neptune interpretation without invoking dimethyl sulfide at all. Ethane, a completely unremarkable hydrocarbon, can produce the same features. So the position in 2026 is this: the biosignature claim is not supported. No independent team has reproduced it. The molecule may well be present in small quantities, which is a different question and remains open. But as evidence for life, it is finished, on 2 counts. It was never reproduced, and it is now known to be made without life in comets, in interstellar clouds, and in models of these very atmospheres. The original group has not retracted, and the disagreement continues in the literature, which is how it should be. What the planet actually is remains genuinely open, and that is worth saying too. 3 readings compete. A Hycean world with a thin hydrogen atmosphere over an ocean. A gas dwarf with a magma ocean, where the atmosphere is the product of hydrogen reacting with molten rock, which would rule out a habitable ocean entirely. Or a scaled-down, metal-enriched gas giant. A conference abstract this year framed the disagreement in its own title as a question of why the atmospheric and interior interpretations disagree so badly. The comparison case tells the same story. A planet called 2OY 270d, about twice Earth's radius, was read in 2024 as a metal-rich mixed envelope by one team and as a Hycean world by another, from identical data. In 2025, geochemical modeling published in the Astrophysical Journal argued it is more likely a rock-dominated planet of about 5 Earth masses that accreted a few % of hydrogen by weight, with all the observed water and methane generated by hydrogen reacting with a magma ocean rather than delivered from outside. The Hycean reading became the minority position without being eliminated. There is one structural observation worth taking away from all of this, and it is not about anybody's competence. 3 independent groups looked at the same photons and disagreed about which molecules were in them. That is a statement about how thin the data is at 124 light-years, using an instrument built for 100 other purposes, at the very edge of what it can do. For about 1.5 years, there was a planet out there that might have had an ocean full of something like plankton. Then, a dozen groups checked the arithmetic, found the same molecule inside a comet and inside a cloud of gas near the center of the galaxy, and the story quietly ended. That is not a failure. That is the only part of this whole subject that reliably works. That test was run and answered. The next one is still running, right now, transit by transit, on the 7 best rocky planets we know. Number 4, 15 transits, in progress. There is one system that is the single most concentrated test of whether temperate rocky planets around red dwarfs can hold on to an atmosphere at all. The results have been arriving planet by planet since 2023, and almost all of them have been negative. And the decisive observation is being taken right now while you are listening to this. TRAPPIST-1 is about 40 light-years away. The star is an ultra-cool dwarf, roughly 9% of the Sun's mass, and about 5/10,000ths of its brightness. It is very old, something like 7.5 billion years, and it flares constantly. Michael Gillon and colleagues announced 3 transiting planets around it in 2016. Then, on the 22nd of February 2017, they announced 7. 7 Earth-sized worlds around one star, which remains the largest single haul of temperate Earth-sized planets ever found. They orbit in 1.5, 2.5, 4, 6, 9, 12, and 19 days, all of them inside 1/10 of an astronomical unit. The whole system would fit comfortably inside the orbit of Mercury. And they are locked in a near-resonant chain, meaning each planet's orbital period sits close to a whole number ratio of its neighbors. That is the fingerprint of a system that migrated inward together and has been stable ever since, and the mutual gravitational tugs are precise enough that they have been used to weigh the planets, which is how we know they are rocky. 3 of them, the 4th, 5th, and 6th out, sit at Earth-like equilibrium temperatures. The 5th, usually just called Planet E, is the target everybody actually cares about. Now the results, in order. Thomas Green and colleagues published on the innermost planet in Nature in 2023. 5 secondary eclipses measured at 15 microns, detected at 8.7 standard deviations combined. Dayside brightness temperature around 500 Kelvin, consistent with little or no atmosphere and no detectable carbon dioxide absorption. Sebastian Sieber and colleagues published on the second planet the same year. Dayside brightness 380 Kelvin, plus or minus 31. A thick carbon dioxide atmosphere ruled out. Then came a lesson in why one measurement is never enough. Elsa Ducrot and colleagues published in Nature Astronomy in 2024, combining eclipses of the innermost planet at 2 different wavelengths. 2 models fitted the data equally well. Either an airless planet with an unweathered volcanic surface, which would imply recent geological resurfacing, itself interesting, or a thick, pure carbon dioxide atmosphere with photochemical haze producing a temperature inversion. That second option is the subtle one. If the upper atmosphere is hotter than the lower, the carbon dioxide band flips from absorption into emission, and the planet looks exactly like a bare rock. Their explicit conclusion was that 1 or 2 broad filters cannot tell those 2 cases apart. Planet D came in 2025. A team led by Caroline Piole-Gorayev published the first full near-infrared transmission spectrum of a planet 8/10 of Earth's size, sitting at the inner edge of the habitable zone. The spectrum is flat. Flat to about 100 to 150 parts per million, no haze slope, no molecular absorption of any kind. That rules out a clear hydrogen-dominated atmosphere, and at high confidence, rules out clear 1-bar atmospheres dominated by methane or carbon monoxide. It also rules out analogues of Titan, of Venus, of early Mars, of Archean Earth, and of modern Earth. What survives is an extremely thin atmosphere, an atmosphere hidden beneath aerosols, or nothing at all. Which brings us to Planet E, and to a genuine ambiguity that has not been resolved. 3 papers published in September and November 2025 reported 4 transits observed in 2023. The findings, the original hydrogen and helium envelope the planet was born with, is gone, stripped away by the star's flares over billions of years. What remains permitted is a secondary atmosphere, one outgassed later from the interior, made of heavier molecules, nitrogen-rich with traces of carbon dioxide and methane, which is to say, Earth-like in character. Or nothing at all. The data cannot tell. And the limiting factor is not the telescope. It is the star. Stellar contamination was present in every one of those observations. Here is what that means in practice. The surface of a red dwarf is blotchy, covered in bright regions and dark spots. When a planet transits, it crosses some of those patches and not others, and the light it blocks is not average starlight. That imprints a signature on the spectrum which looks exactly like a molecule in the planet's atmosphere. It is not noise, which you can beat by observing longer. It is a systematic error which you cannot. So somebody came up with a way around it, and it is the kind of idea that only works in a system with 7 planets. A multi-cycle program described in December 2025 will observe 15 transits of Planet E. and each one is paired with a transit of the innermost planet, taken close in time. The innermost planet is airless. That is now well established. So its spectrum should be perfectly flat. Any structure that shows up in it is the star, and only the star, and can therefore be measured and subtracted from Planet E's spectrum. The star becomes its own calibration reference, using one of its own planets as the ruler. The target is a 5 standard deviation detection of an Earth-like carbon dioxide-bearing atmosphere. The first 3 observations have been reported. The correction is inhibited when strong flares occur during a visit, which is a real limitation. But on the cleanest visit, the contamination was successfully removed, and afterwards, the spectrum of Planet E showed an increased preference for a flat line. As of this month, the full 15 transit result has not been published. The observations are still being taken. Picture what that actually looks like. 1.5 million kilometers from Earth, at a gravitationally quiet point beyond the Moon, a telescope roughly the size of a tennis court sits behind a sun shield the size of a tennis court, pointed at a star so faint you could not see it from a dark field with the naked eye at any distance. It is not taking a picture. It is counting photons and waiting. Out there, a world roughly the size of the one that built the telescope is about to move in front of that star. For a little under an hour, a sliver of starlight will graze whatever atmosphere it has, or does not have, on the way past. Then the transit ends, and the telescope waits again. It will do this 15 separate times. Each pass takes about an hour. Between them, months. That is what an answer looks like from the inside. Not a moment of discovery. 15 appointments spread across years, and a slow accumulation of light. At number 20, we called the dark forest a question with no appointment, an idea built so that no observation could ever settle it. This is the exact inversion. 15 appointments, an hour each, in a calendar, with a threshold agreed in advance for what will count as an answer. There is a broader program running alongside it. 500 hours of director's discretionary time on the same telescope have been assigned to a survey called Rocky Worlds. Its first target was found likely to be a bare rock in 2025, and 4 eclipses taken between September 2025 and April 2026 ruled out a carbon dioxide atmosphere at better than 3 standard deviations. 9 targets have been selected so far, and all the data goes public immediately. And the emerging verdict is worth stating as a verdict rather than a mood. No rocky planet orbiting a red dwarf has yet shown strong evidence for an atmosphere. Not one. Every result so far is either a highly constraining non-detection or genuinely inconclusive. A statistical study published in the Astronomical Journal in June this year argues that the boundary between worlds that keep their air and worlds that lose it may not transfer from our solar system to red dwarfs unchanged, because their ultraviolet output is so much harsher, plausibly leaving most such planets airless. If they all turn out to be bare rocks, this telescope can bound the fraction that hold atmospheres to below 1 in 8, which would matter enormously because the overwhelming majority of the temperate rocky planets we know about orbit exactly that kind of star. That is one system, watched 15 times. The next sign is about turning a sample of 3 into a sample of hundreds, and the machine that does it switched on last year. Number 3. The visitors become a population. At number 16, we watched something leave. An object from another star passed through the solar system, was inside the reach of our telescopes for about a week, and is now permanently beyond every instrument on Earth, with the central question about it unanswered. Number 3 is where that gets fixed. Not by chasing the one that got away. by building something that catches the next one and the one after that, until 3 becomes 30 and an anecdote becomes a population. The Vera Rubin Observatory sits on Cerro Pachon in the Chilean Andes. An 8.4-meter survey telescope carrying a camera of 3,200 megapixels, the largest digital camera ever built. Each single exposure covers more than 40 times the area of the full moon. Over 10 years, it will image the visible southern sky roughly 800 times over. Its first images were unveiled on the 23rd of June 2025, with more than 350 watch parties around the world. Survey operations have been ramping up through this year. How many interstellar objects it will find is a question with an honest and very wide answer, and the width is the interesting part. A study by Hoover, Seligman and Payne in 2022 projected 1 to 3 per year of the size and brightness of the first one. A study by Marchetta and Seligman in 2023 gave a range from 0 to 70 per year, depending on how reflective and how large these things typically turn out to be. Other published estimates land at 5, at 7, and at 21. That spread is not sloppiness. It is honest ignorance, and it comes from 2 specific places. Fast-moving objects smear across pixels during an exposure and lose surface brightness, which costs you detections in a way that is hard to model. And the assumed number density, about 1/10 of an object per cubic astronomical unit, is derived from a sample of essentially 1. The first proof that the approach works arrived before the observatory was even finished. On the 1st of July 2025, a survey telescope at Rio Hurtado in Chile picked up an object at 4.5 astronomical units, inbound. It was designated 3I/Atlas, the 3rd interstellar object ever identified. And when people went back through Rubin's commissioning data, they found it had observed the same object 9 separate times between the 21st of June and the 2nd of July, some of that before the official discovery, and then repeatedly through the rest of July. Then, in June 2026, a candidate interstellar object, flagged in Rubin's survey data, was submitted to the Minor Planet Center. It is an unconfirmed candidate, and it should be described that way, but the pipeline is clearly working. Now the object itself, because the difference between it and the first one is the whole point of this entry. Its orbit is the most extreme ever recorded in the solar system. An eccentricity of 6.145 against 1.2 for the first visitor. An inclination of 175 degrees, meaning it came in almost exactly retrograde, close to the plane the planets orbit in. Perihelion on the 29th of October, 2025, at 1.357 astronomical units. Its speed relative to the Sun, far from the Sun's influence, was about 58 kilometers a second, more than double the first one's. Its nucleus size is bracketed by Hubble observations between about 1/3 of a kilometer and 5.5. Modeling its non-gravitational acceleration narrows that to roughly 1/2 kilometer to 3/4. The coma dominates every direct image, so nothing tighter exists. But here is the crucial difference. It was found 4 months before perihelion. The first one was found on its way out. 4 months is enough time to point everything at it. The James Webb Space Telescope found a gas coma dominated by carbon dioxide, with a carbon dioxide to water ratio of about 7.5, among the highest ever measured in any comet anywhere. Alongside it, water, carbon monoxide, carbonyl sulfide, water ice and dust. Its infrared instrument also picked up a forbidden atomic nickel line at 7.5 microns. That nickel is worth a moment. The coma showed a highly variable nickel-to-iron ratio, with nickel vapor detected far from the sun, out where metals simply cannot boil off rock. The leading explanation involves organometallic carbonyls, nickel and iron bonded to carbon monoxide, which sublimate at low enough temperatures to release metal atoms in the cold. That is not unique to this object. It is extreme in it. Then there is its age. A population model developed at Canterbury and Oxford places its motion through the galaxy in the thick disk, the old metal-poor population of stars that sits above and below the flat plane where the sun lives. The best statistical estimate is around 7 billion years old, with a 68% confidence range running from 7.5 to 14 billion, and roughly a 2 in 3 probability of being older than the sun. If that holds, it may be the oldest object any human instrument has ever measured directly. And the authors of the Webb paper flag honestly that more work is needed to show a carbon dioxide-rich composition is actually compatible with a low metallicity origin in that population. After perihelion, the chemistry changed, and we watched it change. The IRAM 30-meter telescope in Spain observed it on the 1st through 3rd of November 2025 and detected hydrogen cyanide, methanol, carbon monoxide, formaldehyde, methyl cyanide, and carbon monosulfide, with a ratio of methanol to hydrogen cyanide among the largest measured in any comet. And on the 7th of January this year, the Subaru telescope measured the carbon dioxide to water ratio, far below its pre-perihelion value. The object had burned off its carbon dioxide-rich outer layer as it warmed and exposed water ice underneath, which means the nucleus is layered. It has an outside and an inside made of different things. And we watched it peel from 400 million kilometers away over the course of a few months. Hubble imaging through late 2025 and into January this year revealed a prominent anti-tail, a jet pointed toward the sun rather than away from it, extending about 400,000 kilometers. Under image processing, it resolves into one tightly collimated sunward jet, plus 3 smaller ones, modulated by a rotation period of 7.1 hours, with the spin axis pointing within about 20 degrees of the sun. There were techno-signature claims, and they deserve to be handled fairly rather than mocked. Avi Loeb argued from mid-2025 that the object showed anomalies possibly indicating artificial origin, and maintained a running catalogue of them, 18 by March this year, later 22, published on a personal blog rather than in a journal. He urged that raw data be released promptly and that the Juno spacecraft observe the object during its closest approach to Jupiter on the 16th of March this year, at 53.6 million kilometers. The consensus from NASA and from multiple independent teams is that it is a comet. Techno-signature searches using the Allen Telescope Array and a second search at different frequencies by another group found no credible artificial signals. Loeb has since said the object is most likely natural. And every anomaly on his list, the anti-tail, the nickel ratio, the direction of the acceleration, the methanol ratio, is genuinely unusual, and every one has a proposed physical mechanism behind it. Unusual is not the same as artificial. But the questions were asked, the observations were made, and the answers were published, which is exactly what should have happened. Now put the three of them side by side, because this is the argument. The first, in 2017, no detectable coma at all, accelerating with nothing visibly coming off it. The second, found on the 30th of August 2019 by an amateur astronomer in Crimea using a telescope he had built himself, unambiguously a comet from the first night, with carbon monoxide at 130 to 155% of its water abundance, against 0.2 to 23% for comets formed here, read as having formed in a carbon-rich disk around a cool red dwarf. And the third, extraordinarily rich in carbon dioxide, with an anomalous methanol ratio and a probable 7-billion-year-old origin in the oldest part of the galaxy. 3 objects. 3 chemistries. No overlap. The conclusion drawn in the literature is explicit. Interstellar objects are not analogues of our own comets. Each one is a direct physical sample of the conditions in a planet-forming disk around a star nobody can identify, at a time nobody was there to record. They are pieces of other solar systems, arriving free of charge. 1 is an anecdote. 3 is a coincidence. What Rubin is for is the number after that. Those visitors are being counted now. The next sign already got its answer, the fastest resolution on this entire list, and the answer turned out to be us. Number 2, the signal that was answered in 2 years. In 2020, a narrowband radio signal appeared to be coming from the nearest star to the Sun. Within 2 years, it had been killed. And it was killed by the people who found it. That is why it is at number 2. It is the fastest resolution on this entire list, and the machinery built to produce that resolution is, quietly, the most important thing in this video. The Breakthrough Listen program observed Proxima Centauri using the 64-meter dish at Parkes in New South Wales, a telescope now called Murayang, from a Wiradjuri word meaning sky world, and the same dish that received the television pictures of the first moon landing. They watched Proxima for about 30 hours across April and May 2019. The specific detection came from the 29th of April. The signal was designated BLC-1, Breakthrough Listen Candidate 1. It remains the only signal of interest the program has ever produced. Its center frequency was 982 MHz, measured to 6 decimal places. It was a narrow-band tone, sitting in a band where no human transmitter is licensed at that exact frequency, which is why it survived the first automated cuts. And it drifted upward at about 0.04 of a hertz per second. The drift is what killed it, and the reason is elegant enough to be worth following. Nothing in this business sits still. The Earth is rotating, which means the telescope is being carried toward or away from whatever it is pointing at hundreds of meters per second. That imposes a Doppler shift on any incoming signal, and because the rotation is smooth and predictable, the shift changes smoothly and predictably. A signal from a fixed point in the sky has to drift in a particular direction, at a particular rate, at a particular time of night. A transmitter sitting on a planet orbiting Proxima would add its own motion on top of that, with its own signature. BLC-1's drift matched neither. It was drifting, but not the way a thing at that place in the sky is required to drift. The sky has rules, and the signal was not obeying them. The verdict was published in Nature Astronomy in October 2021, in 2 companion papers. Sophia Sheikh and colleagues wrote the one that closed the case. Their conclusion: it is not an extraterrestrial technosignature. It is an electronically drifting intermodulation product of local, time-varying interference. That phrase deserves unpacking, because the answer is more interesting than the jargon suggests. Put 2 radio tones into a slightly imperfect amplifier, and every amplifier is slightly imperfect, and it will generate sums and differences of them. New frequencies, at which nothing in the room is actually broadcasting. The signal was not being transmitted by anything. It was being manufactured inside the receiving equipment, out of other signals. And here is the finding that settles it past argument. The team went looking for others like it. They found dozens of instances of terrestrial interference with the same shape, sitting at frequencies harmonically related to common clock oscillators, which is to say, consumer electronics. Ordinary devices, ticking away at ordinary frequencies, somewhere within reach of a very sensitive dish. Then they went back and observed Proxima for another 39 hours. Nothing recurred. Not an intermittent source. An absent one. There is one further piece of this story that belongs here, because it is about how information travels rather than how physics does. The signal leaked to the press in December 2020, roughly a year before either paper appeared. For that year, the public version of events was that a candidate signal had been found at the nearest star, and the actual version of events was that a careful team was working through a checklist and steadily eliminating explanations. Nobody behaved badly. The gap between a candidate and a result is simply longer than the gap between a rumor and a headline, and it always will be. So why is a failed detection sitting at number 2 on a list of signs we might not be alone? Because the alternative to a field that can do this is a field where every anomaly stays open forever, and where the word unexplained carries no information at all. Those 2 papers are now cited as the best real-world test of a technosignature verification framework, a checklist written before the candidate appeared, applied to it honestly, and followed all the way to a conclusion that nobody in the group wanted to reach. Every entry on this list depends on that being how it works. The wow signal is interesting because 50 follow-up searches found nothing. The Mars sample matters because the confidence scale has 7 steps, and everyone agrees it is on step 1. The dimethyl sulfide claim died because a dozen groups checked it. This is what the machinery looks like when you watch it run to completion on the best candidate anybody has ever had. The system it was pointed at is, for what it is worth, genuinely the best nearby target there is. Proxima Centauri b has a minimum mass of about 1.07 times Earth's, on an 11-day orbit inside the star's habitable zone, 4¼ light-years away. It is the nearest exoplanet to Earth, and it always will be. Proxima d, confirmed in February 2022, weighs about 1/4 of an Earth mass on a 5-day orbit, and is one of the lightest exoplanets ever detected. And the star is the problem. In March 2016, an array of small telescopes recorded the first superflare from Proxima, bright enough to have been seen by the naked eye. The star's optical brightness rose by a factor of about 68, and the total energy released was roughly 10 times any Proxima flare previously recorded. Over the following 2 years, the same array caught 23 more large flares, and the team's estimate was at least 5 superflares a year. Then, on the 1st of May 2019, came the brightest flare ever recorded from that star. It lasted about 7 seconds. During those 7 seconds, Proxima brightened by more than 1,000 times at millimeter wavelengths and more than 14,000 times in the far ultraviolet. A planet sitting 5/100ths of an astronomical unit from a star that does that several times a year has, at best, a difficult time keeping hold of an atmosphere. Which loops straight back to number 13, and the reason a radio measurement of a planetary magnetic field matters so much, because that field is the only thing that would stand between such a planet and its own star. The strongest reason to trust a future detection is that this one was published, examined, and withdrawn. That answer took 2 years and a telescope. The last sign on this list needs neither, because the evidence is already on Earth, and it has been for 3 years. Number 1, the alphabet in the drawer. Everything on this list so far has been waiting on something. A telescope that has not been funded, a mission that has not launched, a spacecraft that has not arrived, a budget vote that went the wrong way, a star that will not stop flaring long enough to let us read the planet in front of it. Number 1 is not waiting on any of that. 2 spacecraft went out, scooped material off 2 asteroids, and brought it home. It is here. It has been here for 3 years. And the answer to whether the chemistry of life is common in the universe is being extracted from it, gram by gram, right now. The first mission launched on the 8th of September 2016 and arrived at an asteroid called Bennu on the 3rd of December 2018. On the 20th of October 2020, it touched the surface for a few seconds at a site called Nightingale, fired a burst of nitrogen gas to blow material up into its collector, and backed away. Bennu turned out to be a rubble pile, a loose heap of fragments held together by almost nothing, and the spacecraft sank into it further than anyone expected. The capsule came down in the Utah desert on the 24th of September 2023. The sample mass was confirmed in February 2024 at 121.6 grams. About 4¼ ounces. More than double the mission requirement and the largest asteroid sample ever returned. 70.3 grams came out in the first pour. The rest was recovered only after the collector head was fully taken apart, which is a small human detail worth keeping. The bulk material is 4.5% carbon by weight, roughly 90% of it organic, and about 0.25% nitrogen. Here is what was in it, published in Nature Astronomy on the 29th of January 2025. Thousands of distinct organic compounds. 33 amino acids, including 14 of the 20 that terrestrial biology uses to build proteins, with glycine the most abundant. Plus 19 non-protein amino acids, many of them rare or entirely absent from known biology. And all 5 nucleobases: adenine, guanine, cytosine, thymine, uracil. The complete letter set of both DNA and RNA in a rock that formed before the Earth had a surface. Exceptionally high ammonia, far above typical meteorite levels. And formaldehyde. Those two together are the classic laboratory route to amino acids, which means the same rock contained both the reagents and the products of the same reaction. The mineral half of the story was published in Nature that same month. An evaporite sequence, 11 minerals precipitated in order out of an evaporating brine. Halite, which is ordinary table salt. Sylvite, which is potassium chloride. And trona, a sodium carbonate, identified for the first time ever in extraterrestrial material. Plus carbonates, sulfates, and phosphates. Which means that on Bennu's parent body, 4.5 billion years ago, there were pools of salty water, and they dried up, and the salt is still sitting there in the order it came out. The results have kept coming. A paper in the Proceedings of the National Academy of Sciences showed the watery alteration was uneven. The parent body was not uniformly processed. A paper in Nature Geoscience reported bioessential sugars, including ribose, which is the sugar backbone of RNA, and glucose. In February this year, carbon and nitrogen isotopes indicated the amino acids formed by more than one root, with glycine apparently made in irradiated frozen ice far out in the cold rather than in warm water on the parent body. And in March, the internal chemistry was found to organize into 3 repeating types of organic mineral region. And then there is the second sample, from a completely different asteroid, and it agrees. A Japanese mission returned material from an asteroid called Ryugu on the 6th of December 2020. 5.4 grams. Extremely dark, about 2% reflectivity, darker than charcoal. About half porous. Dominated by water-bearing clay minerals and containing grains of stardust older than the solar system itself. One of its 2 collection attempts fired a projectile into the surface first, specifically to reach material that had never been touched by sunlight, Yasuhiro Oba and colleagues published in Nature Communications on the 21st of March 2023 uracil at 6 to 32 parts per billion and nicotinic acid, vitamin B3, at 49 to 99 parts per billion. Because that material was collected directly from the asteroid and sealed there, terrestrial contamination could be excluded for those specific compounds. And in March this year, a Japanese team reported that Ryugu contains all the DNA and RNA nucleobases as well, with the yields correlating with ammonia concentration, which links the ammonia-rich chemistry found on Bennu directly to how many nucleobases a body ends up carrying. 2 spacecraft, 2 unrelated asteroids, the same inventory. Now the cautionary tale, told in full, because it is the most misreported result in this entire field. A team led by Matthew Genge published in Meteoritics and Planetary Science online in November 2024 under the title Rapid Colonization of a Space-Returned Ryugu Sample by Terrestrial Microorganisms. A grain about a millimeter across developed carbonaceous rods and filaments, matching the sizes and shapes of filamentous microbes, sitting right alongside the indigenous organic matter. Their abundance rose and then fell over time, implying a living population with a generation time of 5.2 days. The conclusion is the exact opposite of the headline that usually gets attached to it. This is an ordinary terrestrial microbial community that colonized the fragment within days, despite hermetically sealed transport, a nitrogen-filled cleanroom, and sterilized tools. It is not life from an asteroid. It is a demonstration of how quickly Earth's biology gets into anything we bring home, and a permanent argument for handling every future sample as though the answer depends on it. Which, at number 7, it does. For comparison, there is the reference sample against which all of this is judged. The Murchison meteorite fell in Victoria, Australia, on the 28th of September 1969, and about 100 kilograms were recovered. Its amino acid count depends entirely on the method used to look. Early work found 5 protein amino acids and 12 others. Later, tallies give 52, then about 70, then 86 by 2017. The largest left-handed excess ever reported in a meteorite is a compound called isovaline in Murchison at 18.5%. And this is where the story turns. Every amino acid used by life on Earth is left-handed. The mirror image versions exist and are chemically fine, and life does not use them anywhere, in anything. Why has been an open question for a century. That 18% excess in Murchison was, for decades, the best argument that space handed Earth its handedness, that life is left-handed because the delivery was. Bennu's amino acids are essentially racemic, equal parts left and right. Ryugu's are racemic too. Careful analysis of pristine material from both, published in 2025, directly challenges the idea that an early bias caused terrestrial homochirality. If space delivered a 50-50 mixture, then life's exclusive left-handedness had to be produced here, on this planet, by something that happened after the delivery. That is contested, and the lean this year is that it is terrestrial in origin. So let us be precise about what all of this proves, because the precision is the point. 2 spacecraft went to 2 unrelated asteroids and brought back the same inventory. Amino acids, all 5 nuclear bases, sugars, including the one RNA is built on, ammonia, formaldehyde, and the mineral record of standing water that evaporated. The chemistry that comes before life is not rare, not fluky, and not special to this solar system. It is a default product of the way planetary systems form, which means it is presumably a default product of the way other planetary systems form too, around stars nobody has named. And let us be equally precise about what it does not prove. Monomers are not polymers. No peptides, no proteins, no strand of RNA or DNA, no self-replicating molecule of any kind has been found in any returned sample. Only building blocks. Assembly is the unsolved problem, and it is severe. Genetic polymers are energetically expensive to make, and there is no agreed chemical mechanism for assembling functional RNA out of loose monomers without a highly structured environment doing the organizing. The two competing models of how life started each require exactly what the other was supposed to supply. And contamination, as Ryugu showed within days of being opened, is a live methodological threat to every claim anybody makes in this field. The asteroids delivered the alphabet. They did not deliver a sentence, and nobody knows who wrote the first one. Picture the room where this is happening, because it is the last thing on this list, and it is not what you would imagine. A clean room, a nitrogen atmosphere, glove boxes along one wall, a tray, and on the tray a few grams of black grit that has never once been rained on. Somebody in a suit and gloves moves a single particle with a tool finer than a needle under a microscope and photographs it before it is touched again. Everything in that room exists to keep the Earth out. The grit is 4.5 billion years old. The building is 50. Somewhere in that tray are the letters of both genetic alphabets, more than a dozen of the amino acids that make every protein in every living thing on this planet, the sugar that RNA is built on, and the salt left behind by water that dried up before the sun had planets. And it is not going anywhere. There is no launch window. There is no gravity assist. There is no budget vote. It is on a shelf. Most of it is deliberately unopened, set aside for instruments that have not been invented yet. The same logic as the witness tubes on Mars, the same care applied in advance. The only variable left is how carefully and how slowly someone looks. That is the whole descent. An argument that no observation could ever test. A catalogue of stars with a clear view of us. 72 seconds in 1977 that never came back. A residue of sightings that dissolves whenever the sensors improve. One visitor that left before we were ready. Bursts we are still learning to place. 6,000 worlds. A magnetic field we cannot yet measure. A pollutant we could see if the telescope survives its budget. An ocean with everything it needs and nobody coming. A moon with rain made of methane. A gas above Venus that will not resolve. An ocean under 30 kilometers of ice with a date in 2030. A rock in a tube with no ride home. A gas two machines cannot agree about. A claim that was made and then withdrawn. 15 appointments still being kept. A telescope in Chile turning 3 into 30. And a signal that got its answer in 2 years, and the answer was us. And then a drawer in a building in Houston and a sealed chamber outside Tokyo holding 121 grams and 5 grams of 2 asteroids that turned out to be carrying the same ingredients as each other and as us. It is number 1 not because it is proof. Nothing on this list is proof. It is number 1 because it is the only entry where the waiting is nearly over. Sleep well and good night.